Howdy y'all, it's the Diabolic VTutor, and today we're going to be covering trig graphing. So unfortunately, we're still stuck on the old trig. But let's get started. So here we are, we're basically going to be working on the tangent functions. I'm sorry, not the tangent functions, the trig functions. So sine function, graphing that one, the cosine, and then the tangent. And if time permits, we'll go over the reciprocal functions as well. So yeah, we can cover this one, that one, and that one. And we're going to be graphing it not in terms of the, what was I going to say about that? No, that's fine. So again, these are the ones we're going to be working on today, primarily, and again, maybe go on to the reciprocal functions. Alright, so we already know that when we're working with something like the sine function, there's some sort of a periodicity to the function. Let's just call it y for now. So y is equal to sine of x. And then as we've learned so far, the arguments for this particular function are just going to be angles. Not necessarily coming from right angles, but that's like the most prominent application, at least when you're in high school math. So we have the arguments, and then the angles go into the arguments, and then we made note that there were some things called coterminal angles, where if you input certain degrees, you can input other degrees that are going to be equivalent and grant you the same ratio given the trig function type. So what I mean by that is, for example, if you have sine of 90 degrees, or let's do radians. So instead of 90 degrees, pi over 2. So if you input pi over 2 as a argument into the argument for the sine of x function, then what's going to happen is you're going to get a return value, and then the return value is going to be 1. So plugging in pi over 2, you get an output of a 1. And then the one coterminal angle to pi over 2 is to simply just add 2 pi to it. So that's full circle from the base angle, and then we're going to get something like 5 pi over 2. So what we mean by periodicity is if you plug in a value like 5 pi over 2 into this base function, you will also get 1 for the situation. So there's a return to values. This one returns an output of 1, and then this one also gives you an output of 1. So as we keep inputting more and more values, as we are increasing the value of the x, we're going to hit the same values over and over again as time goes on. So that's what we mean by the periodicity of the function. And the same is true for the cosine and the tangent. The tangent having some weird exceptions, of course, because it's a fraction. So let's get to this one first, our most basic trig function for graphing. It's going to be the sine function. We're going to have our x-axis and we're going to have the y-axis. And what I like to do for this type of graphing is just put 4 hash marks, and then we'll see why maybe later. So 1, 2, 3, and 4. For this one, we ask ourselves, what's full circle? Full circle for your base function is from 0 radians to 2 pi. And why do we have 4 hash marks? Because when we are graphing it in the other way, using the reference angle, recall that this one is going to be an interquadrant angle, that's going to be 0. This one's going to be another interquadrant angle, pi over 2. So is this one, that's going to be just pi, and then this one is going to be 3 pi over 2. So when we draw our triangles for the reference triangles, we make note that there's some sort of repeating values of sorts. So there's going to be 1 to 1 to root 2 for the 45, 45, 90. And then when you get to here, you also make note that there's kind of similar values. And then when you get to this particular reference triangle, also similar values. Not totally the same, but very similar values. Well, then once we reach the full circle, we get back to the original 1 to 1 to root 2, for example, if we're doing 45 coterminal. So just to reiterate, we have 4 hash marks here because it's nice. Those are nice interquadrant values for our sine functions. So for the smallest positive ones, that's going to be 0, pi over 2, pi, and 3 pi over 2. This is referred to as the period of the function, because that's when the function resets. And what do we mean by that? So looking at the 0 input. So if x is equal to 0, that's interquadrant angle number 1. And that's the collapsed triangle. And when you're dealing with the collapsed triangle, it has no opposite for this one. So thus, sine is going to give you a value of 0. So right there, I'm going to do a little bit of a table chart for now. And then we're going to drop the table value afterwards. But this is x value, and then we have our output value. I'm going to write y for this one. So if x input is 0, then the y output is also going to be 0, because we have the collapsed triangle of 0 over r, where r is not 0. Again, this is the interquadrant angle, one of them. And of course, if we get to the next interquadrant angle, we're going to be skipping by the 45, 45, 90. We're going to be skipping the 30, 60, 90 and the other ones. Jumping straight to the next interquadrant angle. So this one right here. And in this situation, for this interquadrant angle, that's when the opposite is equal in magnitude to the hypotenuse. And they're both positive. So when the opposite is equal to the hypotenuse, then you have a 1-to-1 ratio. So the output is going to be 1. So if sine input is pi over 2, interquadrant angle, and then the output is just going to be 1, positive 1. And at the moment, I don't have any hash marks for the y-axis, so let me put the hash mark right there. It's not exactly to scale, but that's okay. So there's going to be positive 1, and this is going to be negative 1. And I'm not going to put any more hash marks greater than 1 for this moment, is because the value, the output for the sine function as a base function is just going to hover between two values. It's going to be hovering between negative 1 and positive 1, because at the most basic form, the ratio between the opposite and then the hypotenuse will never be greater than 1, because how can you have an opposite side that's greater than the hypotenuse? If you sketch out a right triangle, for example, there's no way you can make this one longer than this one. Then we wouldn't have a right triangle anymore for the situation. So that's a good, helpful thing to think about in terms of why this function hovers between negative 1 and positive 1, but let's not emphasize that too much for now. All right. So plotting the second point, if again the x value is pi over 2, then the y value output is 1. So this first hash mark, that's going to be pi over 2. So for that interquadrant angle, the ratio is 1-to-1. So right there. Just color this in red. Alright, then for the next one, next interquadrant angle, that's when we have the pi. That's when we have a collapsed triangle with 0 opposite again, but then the hypotenuse exists. So we get a 0 over 1, so we're back to 0 for the output. So again, for this interquadrant angle, if x value input is pi, then the y output is going to be 0. I think I need to open the door for my roommate. I'll be back real quick. Okay, I just went to open the door for my roommate because it's raining. Oh, we're back. Whoops. So far we only graphed 3 points. We've graphed the red point, the magenta, and then the blue point, and now we just need 1 more point to complete. Well, actually, no, we need 2 more points until we hit reset value. So again, this is interquadrant angle value number 1, interquadrant angle value number 2, and then this is going to be number 3. We're right here. So we're going to move on to that particular interquadrant angle, this one. So when x input is 3 pi over 2, what happens for that one? So we have the we have another collapsed triangle where the opposite is equal in magnitude to the hypotenuse, but it's pointing down the y-axis, so it's going to be -1 to +1 ratio, thereby leading us to -1. That's because the opposite is equal in magnitude to the hypotenuse. So it's a 1-to-1, but then because it's going down the y-axis, it's going to be negative. So that's why I have a negative right there. So graphing this particular orange point, it's going to be, once we hit the third interquadrant angle going in some sort of order, the output is -1-to-1. So right there. And now we hit the reset, and by reset meaning what happens? The ratio is exactly collapsed triangle again, so it's 0 to radius, which is not 0. So like this. So reaching full circle 2 pi. Full circle because this is the default sine function. We're going to get an output value of 0. So again, do make note of the periodicity. We start from 0, we go to 1, go to 0, to -1, and then back to 0. And what's going to happen is we can connect this as smoothly as possible. And you just have to trust me for the moment. But if you decide to connect these as smoothly as possible, it's going to look something like this. There's a sort of concave down. And switch transitions to concave up. And because, again, there's a periodicity to this particular function, we're going to be copying this exact same motif. So let me show you real quick. So I trace the graph, and then what's going to happen is if you decide to put more evenly spaced hash marks, you're going to get this exact same thing. And if you continue onwards and onwards, I'll just copy, hold on. You get the exact same thing. So that's why we talk about the periodicity of this particular trig function. Same is true for cosine, because if you decide to continue to graph it, it's going to be repeated the same thing ad nauseum. So this is the recurring motif. So start off at 0, hit some sort of maximum value of 1 for this base function, goes to 0, goes to -1, resets back to 0. To begin the cycle again, it's maximum, 0, -1, resets back to 0. And by resetting, it means we're prepping for the same motif yet again. So this right here, just because it hits 0 at that particular node doesn't mean that that's the period, because you don't repeat this motion again. It's hits the maximum, 0, minimum, reset. Maximum, 0, minimum, reset. So this is what we refer to as a full period. So that's going to be a bunch of vocabulary words. So period is basically how long it takes for your function to quote-unquote reset, at least in my terms. Some people attribute it to the length between one peak to the next peak, which is the same length as the one we just specified from here to there. Or you could talk about the period, the reset value from trow, the bottom of the graph, to the next bottom, which is right there. And that's going to be 2 pi. Same as this one, 2 pi, which is the same as this one, That's 2 pi. So 2 pi is the magic number for this one. This is not anything new to memorize because full circle is 360 degrees, or 2 pi, since we like radians here. But if you like degrees, then we'll put 360 degrees right here as well. So that's what we mean by full circle, because we're going to hit the same ratios over and over and again, because this is a cyclic motion. This is a periodic motion which captures the cyclic nature for those ones right there. Okay. I don't think that was the best explanation, but that's okay. We try our best. Let's get to graphing other things, of course. Again, we're just show you standard procedures when we're dealing with something like sine again. Let's just repeat this one. So we have the interruption accounted for. So we're graphing this basic one. I just like to put 4 hash marks, 1, 2, 3, 4. The fourth one is going to be full pi. I'm sorry, not full pi, full circle. So it's going to be 2 pi because nothing special is happening to this base sine x function. So full period is from 0 to 2 pi. This one is unmodified. So our function will hover between two values. It's going to hover between +1 and then -1. So when we start to graph this, it starts off at 0, 0. When it hits the first hash mark, which is going to be pi over 2, it's going to hit the maximum of 1. Because again, this is the interquadrant angle. You don't have to memorize this, but it's nice if you do. If you don't, then you just have to sketch out the situation. And if you recall this one right here, interquadrant angle, it's when the opposite is equal to the hypotenuse. And it's going upwards, so it's +1 to 1. So hence, 1. And then going through the other interquadrant angles, this is the second one that we're going to hit. So it hits back to 0. This is the third interquadrant, hits the minimum -1. This is the reset value. We go back to 0. And then you just take this motif and then you just copy paste it. So if you're deciding to go into the negative zone, we're going to have a -1. I'm sorry, -pi over 2. And this is going to be -pi, -3 pi over 2, and then -2 pi. Just take this motif and copy it, kind of going backwards. This is a 4 hash marks. So 1, 2, 3, 4. Just copy this exact same motif. We'll start off on the fourth one. Start at 0, go up, maximum, 0, minimum, reset value. Now this isn't perfectly to scale because I kind of drew it over this one right here. So let me correct it just a little bit. So try not to exceed the, don't exceed the maximum. Because again, we can't get a ratio of over 1 to 1 for this situation. So 0 max, minimum, I'm sorry, not minimum, 0, and then hit minimum, and then reset value. And that's it. That's all you need to do to graph the sine function. So let's get to something that's a little different. And then thankfully our graphing rules will carry over from before. So all our shifting rules, the left-right translations, we have our up-down translations, those are all going to be the same thing, except you just need to be mindful of the hash marks. So here's what I mean. So if you're dealing with something like y is equal to sine of x, and this is going to be -1. This is outside of the trig function, so the entirety of the graph is just moved downwards by 1 space. This is the base sine function. Nothing special is happening to the x, and there aren't any special modifiers in the front. So standard procedures, 1, 2, 3, and then 4. And because there's no spelled out number in front, there must be an invisible 1. So our max value for our sine function is going to be +1, and the minimum value for our base sine function is going to be -1. Make note that there's a modifier of -1, so that's a downward shift. So all values will be moved downwards. So immediately I put a second hash mark right there. because normally this is our lowest point. But because we have a downshift of 1, we're going to have lowest point of negative 2. Same procedures as before. Full circle, full period is 2 pi. This is half circle, and then this is going to be pi over 2. This is going to be pi plus 1 hash mark. 1 hash mark is going to be pi over 2. So to label this one, it's just going to be 3 pi over 2. Because you're just adding this one plus this one to get to this one. So 4 hash marks, minimum. We should be good to go for graphing this one. So typically we start at 0, 0. We're going to be hitting max 1, 0, hit minimum negative 1, reset value. But we have a downshift of negative 1. So here's what happens. Again, normally for unshifted function, if we ignore this part right here, just sin x base function, we're going to start 0, go to 1, 0, minimum, reset. But since we have a minus 1, everything is translated one space downwards. All y values are decreased by 1. So here we are. That's it. We already know these graphing rules from when we graphed our parabolas. So downshift. So you can imagine what's going to happen next when we deal with this type of situation. Suppose we have something like this. So if you see a number like this, we are familiar with this rule. It's just going to be one space shift over to the right. But because these are angle arguments, we're not going to have weird shifts like -1 usually. But typically it's going to be shifting by nice radians. And what I mean by that is instead of having -1, which you could possibly get that, but it's uncommon. Most teachers will give you nicer values than this one. So -1 as a shift inside the argument is not a nice shift. So something like minus pi over 2 is nice. So this one right here is just 1 hash mark where we're working with our base function. So let's see. So I'd just like to put down 4 hash marks again. 1, 2, 3, 4. Nothing as special is happening to the x, at least ignoring that for a moment. So there aren't any multiplication things onto the x. So we have something called standard period. In order to reach full reset value, it just takes a total distance, a total rotation of 2 pi. So standard 2 pi. And then you can fill out the rest of the hash marks if you wish. Let's do it. Pi over 2, pi, and then 3 pi over 2. Invisible number of 1, so we have a max value of 1 and a minimum value of -1. So if we ignore this minus pi over 2 modifier inside the argument, standard procedure, start at 0, 0. For the first hash mark, hit max. For the second hash mark, go to 0. For the third hash mark, minimum. For the fourth hash mark, reset. Back to 0, 0. So what does this minus pi over 2 do? Well, that's just going to be a shift. Since it's associated with the x, it's a left or right movement. Since it's a minus, we're in opposite land, so we move pi over 2 spaces forwards, which by our scale is simply 1 hash mark. So you take all the anchor points and you just move them, you move them 1 space over to the right. So make note. Let me emphasize the point. Let's emphasize this one right here. So just to make things a little more explicit. So pay attention to that red point. That's going to be the anchoring point for now. All we have to do is drag it 1 space over, 1 hash mark space, which is equivalent to pi over 2. And then there we go. That's it. That's all we got to do. Let me just make this more to scale. Okay. And there we go. That's like essentially how we graph this sort of situation. Obviously this is incomplete, so we should copy this motif. So it's going to be look something like this if you go on forwards. If we go leftwards, if we need more graph to the left, then just count 4 hash marks. This is already 1 hash mark. So 2 hash marks, 3 hash marks, and 4 hash marks. I like doing 4 hash marks at a time because that's related to rotational full circle. Okay, so 1 hash mark is not enough. This is 2nd hash mark, 3rd hash mark, 4th hash mark, reset. So graphing by 4s is really nice. Which means that for our graphing, just go backwards, okay? Just copy them as motifs. Since we're moving to the left, we start with this lower point, so concave up. So towards the first hash mark, we hit the -1 minimum. And then towards the second one, we hit 0. Towards the third one, we hit the maximum value of +1. And to the fourth one, we reset back to 0. If you want to be a little artsy, we just do one more half one right here. This is going to be 1 hash mark. It hits the -1 right there. So if you imagine this is on a viewing window for a graph, it's going to look something like this. And that's it. Nothing magical. It's pretty nice. At least that's what I think. So let's put those two things together. So we're going to have a horizontal shift and we're going to have a vertical shift. No amplitude change. In other words, there's no number out in front. So there's an invisible 1 in front of our sine function. There isn't a shown value in front of the x. So there's going to be invisible 1 in front of the x. We're going to have plus pi. So this is going to be our shift. And then we're going to have minus. We're going to have plus 2. So already we can see what's happening. So from our parental function, which is just going to be sine of x, we have a transformation, we have a translation left to right, and then we have a translation up or down sort of situation. But again, same rules apply as before. Since it's plus inside the parenthetical with the x, if it's associated with the x, we're kind of opposite land. So it's going to be shift pi spaces to the left. This one's outside of the function that we're considering, the main function, so that's plus 2. All the y values get increased by 2, so hence a vertical shift upwards by 2 spaces. This is just parental. So let's get to graphing. X-axis, y-axis. I just like to put 4 hash marks. 1, 2, 3, 4. This is going to be 2 pi. Again, invisible 1 in the front, so we have a max value of 1, a minimum value of -1. Again, these ones come from the ratios. If we were to graph just this one, it starts off at 0, 0, hits max, 2nd hash mark goes to 0, 3rd hash mark hits 0, 4th hash mark, it goes to reset. So let's take into consideration our shifts now. Well, first, we need to put more hash marks. Since we move everything upwards 2 spaces, this maximum, which was at +1, needs to go to +3. So this is 1, this is 2, and that's 3. And then everything moves 2 hash marks over to the left, so I'm going to have to need some negative hash marks right here. So we're going to put 1 hash mark and then 2 hash marks. I'm just going to put 2 hash marks because we have a shift of pi, and then by this particular scaling, since each hash mark represents pi over 2, then 2 hash marks represents a shift of pi. So this tells us to move over 2 hash mark spaces. So let's go back to our orange graph right here. So just for the parental sine of x unshifted, we have it right there. If we take into account the plus pi inside the argument, then we're going to shift 2 hash marks over. This is just going to be 1 hash mark or pi over 2 shift. This is going to be 2 hash marks, so that's going to be a pi shift to the left. Unfortunately, these hash marks aren't exactly perfect, so I'm just going to fudge it just a little bit to make it look nice. Okay, there we go. And that's it. That's all we have to do for this particular graphing, but We should probably do a little bit more than this, because if we cut it off right here, it seems like it doesn't go on forever. So for the next two hash marks, starting from here, again, this is reset value. So we're going to go up to max value for this hash mark. Once we move over to the next hash mark, it goes back to 0. Now let me make that a little smoother. It's going to be max value of 1. Shift it. First hash mark is going to be positive 1, and then next hash mark movement is going to go back to 0. So that's pretty nice. If we wish to do more right there, we're just going backwards to the left. So let's put the hash mark. Maybe 2 if you're feeling like it. So if we're expanding the graph over to this section right here because it looks kind of barren, then next space over, we're starting at 0, so the trajectory is downwards because we already hit the max. So for this hash mark, we're going to hit the minimum, which is at -1, prior to this +2 shift. So we only considered this one and the base sin of x function so far. And once we hit this one, that's the minimum. So when we move on to the next hash mark right here, we're going to hit back to 0. So there it is. So if you want to expand this one, we start off from the max, so the trajectory is to go to the minimum. So from this hash mark at 0, next hash mark over is going to hit the minimum, which is -1. So now the graph is looking a little more populated, so it doesn't look like we're just kind of skimping on work. So now let us take into consideration the shift upwards of 2 spaces upwards. So all I gotta do is pay attention to one anchoring point, where I'm gonna make this one the anchor point. This is a maximum of 1. You know what? Let's make this one the anchor point. So this one is currently at 1. That's a maximum value for this particular function, only from here to there. So when we put the +2, everything moves upwards 2 spaces. So we're going to drag this entire graph 2 spaces upwards. So that's 1 space upwards, and then 2 spaces upwards. So again, starting from this initial position, keep track of the anchor points. 1 space upwards, 2 spaces upwards, and then we're good to go. If you're feeling particularly paranoid about your function, your graph hypothesis, all you need to do is check it by plugging in a value. So unfortunately, again, this one is not perfectly to scale, so I'm going to have to fudge it just a little bit. So according to our graphical hypothesis, this point here is predicted, and this point here is located at pi/2, 1. So this is our graphical hypothesis. This is the actual function, so therefore, if we plug this one into here, then we should expect to get an output of +1. So let's try that. So again, we're just testing our graphical hypothesis by plugging in this data. We're going to test this prediction made by this particular hypothesis. So here we go. We take the y is equal to sin of x, but we're plugging in a specific value of pi/2. Because we want to test our graphical hypothesis. The argument is modified by +pi. And we have a shift +2 on the outside. So we expect, according to our graphical hypothesis, we expect a value of 1 for this x input. So we predict 1. So mashing those two together, we get 3 pi/2, which is just interquadrant angle pointing downwards. If you take sine of that, it's going to be -1. So the question is, will that be equal to +1? Well, again, this one, it's just going to be -1. Interquadrant angle pointing downwards. Modified by +2. So it is indeed going to be +1. So our graphical hypothesis is consistent with the data, so we have great confidence that this graph is correct. So let's put the viewing window just to make it look nicer. There shouldn't be any breaks in your graph. This is just a consequence of my drawing, but this one should be filled. and try to make it as smooth as possible. And then that's going to be it for this particular sine function. As you see, not too bad. But let's talk about the concavities just for a moment. So let's go back to the base function y is equal to sine of x. So again, when graphing these 4 hash marks, 1, 2, 3, 4. This is unmodified x, so full period is going to be 2 pi. That's the reset, aka full circle. This is just going to be 0, 0. We'll graph this nonsense. It starts off at the maximum. I'm sorry, it starts off at 0, 0. Because sine of 0 is 0. Next space over is a maximum of 1. Let me put the y-axis first. It's positive 1, negative 1. So when graphing these, this is going to be smoothly like this, hits the maximum right here. So how do we know it's going to be something like this? Well, unfortunately, you're going to have to trust me on this, but you don't have to fully trust me on this. So what we can do is we can plug in a half hash mark. So from here to there, from the standard hash mark, that's going to be a total of pi over 2. So half of that is going to be pi over 4. And this one should be very familiar to us. That's one of our good old friends. Special right triangles. So in terms of this other graph, in terms of graphing our reference triangles, pi over 4 is right here. It's halfways between 0 and pi over 2. So it's going to be the classic 45, 45, 90 reference triangle. So the ratio is 1 to 1 to root 2. So what's going to be sine of this particular pi over 4? We're already familiar with this. It's going to be root 2 over 2. That's exactly the point that's being hit right there. So we make note that root 2 over 2 is going to be greater than 1 over 2. Because 1 is the square root of 1, so this makes it easier for the comparison. We can see that root 2 is greater than root 1. We have the denominators are equivalent. So in other words, the point is up here. It's not down there. So it's not going to be something like this, for example. So when we graph pi over 4, not here, but a little greater. So that's going to be our guide in terms of reconciling the situation. So we know that the graph doesn't do something funky like this, because that would imply that the pi over 4 leads to an output that's less than half, which is not true. And then you can see the same thing that's happening if we go to the next half hash mark. So if we look at the y output for this one, what's this particular point? It's going to be half a hash mark space over, which is going to be pi over 4 plus pi over 2, which takes us to 3 pi over 2. I'm sorry, 3 pi over 4, which again should be fairly familiar to us. That's going to be the 45, 45, 90, except in the second quadrant. But we make note that the opposite is still positive 1. It's just the adjacent that's negative 1. But that's not what we're concerned with. That's the sine function. So it returns back to root 2 over 2. So when we decide to graph this one, trace the graph, we make note that it's not going to be something like this. Because that would indicate that's half. But this is greater than half. So rather than putting the point right here, the point that we plot is actually a little higher up. So hence, like this. That's why we don't have a dip downwards like this one. And then you can kind of keep plugging in points if you wish, just to verify this one. If you plug in halfways between these two, you're going to get something that's not directly between them. Something a little bit higher, like so. So that's why it leads to this concave downwards appearance. But don't worry too much about concavity unless you're in AP Precalculus or AP Calculus. This is just strictly Algebra 2 analysis, or maybe from typical Precalc. Alright. So that's why you don't have to fully trust me. You can just literally check the data table yourself. So if this is perfectly linear, then we always have a constant decrease, but we don't. Rather, we have this sort of a increasing, decreasing rate. Again, don't worry too much about the vocab. It's going to be eventually curve around to this one, to the next major hash mark, not half hash mark. We hit the minimum. And then one full hash mark over, back to reset value. Again, you can test out these half hash mark points. So the distance from here to here is pi over 2, which takes you to one of those 45, 45, 90s. It takes you to root 2 over 2. Same thing right here. It takes you to like a root 2 over 2, but it's going to be negative. So past halfway point. This graph isn't totally to scale, which is why things are a little finicky. But that's the main idea anyway. I hope that makes sense. So let's clear this real quick. Alright. So that's the intro to the sine function. The cosine function is mostly going to be the same thing. We're not going to talk about the tangent function just yet. We're just going to be talking more about the sine function. Because if you know how to graph the sine function, you pretty much know how to graph the cosine function. If you know how to graph the sine function, then you pretty much know how to graph the cosecant function. It's a little bit of a tailoring, but it's essentially the same thing. So, one stone, three birds, right? Let me take a quick sip. And we'll talk about amplitude changes, and we'll talk about period changes and all that nonsense. Okay, so when we talk about the amplitude change, it's pretty much going to be like vertical stretch. Unfortunately, vertical stretch isn't a very nice term for this one, because there's some peaks pointing downwards. But let me just first draw our attention to the parabolas. So if you recall, y is equal to x squared. When we look at something like this and we decide to graph it, it's going to be the classic situation. Start at 0, 0, 1 to 1, and then 2 to 4 type of movement. If you recall from earlier days, connect those as smoothly as possible. It's perfectly mirror on the other side, so negative 1 to 1, negative 2 to positive 4. So that's the base function with an invisible number of 1 in the front. And we make note that this is called this affects the vertical stretch or the vertical compression of our graph, because this one essentially modifies outside of the squaring function. So what that means is if we have a value of something like 2 in the front, all it does is it multiplies all our y outputs by 2. So everything is now doubly as tall. So 0 times 2 is still 0. But then 1 to 1 movement changes to a 1 to 1 times 2. So this point is now twice as high because of this modifier. Same thing for this one. Instead of being 2 to 4 movement, we have 2 to 4. 4 is the output, modified by times 2. So that takes us to positive 8. So hence our new graph. So this is referred to as the vertical stretch. We make note that this one doesn't stretch below because 0 times 2 is still 0. So that's essentially a stretch. And of course, if we have something like a modifier like 1/4 in the front, then everything gets vertically squashed. So instead of being, well, first if we graph 0, that's still going to be 0. Because 0 squared is 0, and then 0 times 1/4 is still 0. But if x value is 1, for example, 1 squared is 1, but now we reduce it by a fourth times a fourth, so it just ends up being a very tiny value, 1/4. Instead of being a 2 to 4 movement, it's going to be 2 to 4 movement times 1/4. So this collapses from a 2 back down to a 1. So this is referred to as a vertical compression. So the blue one is a compression, and then the red one is a stretch, and then the orange one is just default skin. Very boring. So I'm reintroducing this idea because it's going to be nearly the same thing when we're doing our sine functions. So y is equal to base invisible 1 sine of x. So that's going to be orange. So let's get to graphing that nonsense. Hope you've memorized it by now. So sine. If you want to have some sort of nifty mnemonic, you can memorize this. If you're familiar with this, if you're familiar with a particular story, it's something called original sin, origin, sin, sine. So you start off at 0, 0. So origin, original sin, right there. If you like to memorize mnemonics, and then we have 4 hash marks over. So 1, 2, 3, and then 4 full period. This is unmodified period because it's just a boring old x within the sine function. So those are the parentheticals, unmodified x. So we have a default reset value of 2 pi. And then of course there are no horizontal shifts, and then there aren't any vertical shifts. And then we have an amplitude of default 1. So let's put the maximum of 1 here, and then the minimum -1. Because again, the sine function always hovers between -1 and +1, because those are ratios. If you imagine forcing in right triangles, the ratios will always be fixed. The opposite side of a particular right triangle will never exceed the length of the hypotenuse. So, very procedural. First hash mark, maximum. Second hash mark, 0. That's just one of our interquadrant angles. The third hash mark, -1. That's the minimum. And then fourth hash mark space, that's going to be full circle, so we reset back to 0. Alright, so that's the boring situation. So what if we have an amplitude change? In other words, we have a number in front. So suppose we have 2 in front of our sine. For the most part, it's going to be the same thing as what we've seen with the parabola. So the zeros are unmodified because 0 times 2 will still give you 0. So these, I refer to these as the nodes. I think other people call them nodes as well. Nothing happens to the nodes because they're at default 0. Because 0 times 2 is still 0. What's interesting is this one right here, the maximum value of 1 for the default function. Everything's increased by times, it's now twice as high because it's times 2. So instead of being a 1 hash mark movement to 1 for the y value, it's going to be 1 hash mark over first inner quadrant to 2. So instead of being 3 hash mark movements and then 1 value of -1 for the y value, it's going to be 3 hash marks over, 2 hash marks down for this particular scaling. So this one, for parental, was 1 times 1. But now for this one, it's 1 times 2, which leads us to 2. Instead of being this -1 output, it's going to be -1 times 2. Taking this down there. Nodes are still the same thing because 0 times anything is still 0. 0 times anything is still 0. 0 times anything is still 0. Then you connect them as smoothly as possible. Make note that this is going to be concave down. This is like the mouth of a cave. This one is going to be concave up. Hit the minimum. Reset back. And that's going to be the amplitude change. All that changes is the highs and the lows for this particular base function. that's it. Nothing too spectacular. So you can imagine what happens if we have, guess what it is, a fractional coefficient that's less than 1 but greater than 0. So let's do an easy one. 1/2. Now let's do 1/3 just to make things a little more interesting. So 1/3, you can imagine what's going to happen for this one. So instead of being a default 1 to 1 hash mark, it's not going to be positive 1. It's going to be half of that, which is 1/2. 3 hash marks over, instead of being -1, it's going to be -1 times 1/3. So 1/3 as low. So this is a full -1 down. That's 1/3. This is 2/3. So this is going to be -1/3. The nodes are unmodified because 0 times 1/3 is still 0. 0 times 1/3 is still 0. And then 0 times 1/3 is still 0. Connect them as smoothly as possible. This is concave down, and this one's going to be concave up. You can verify this by plugging in half hash marks. But if you don't, that means you trust me on this, which you shouldn't always do. So there we go. So that's going to be the graph for this particular modification with an amplitude change of 1/3. That's all that's going to happen. So let's put those three ideas together and let's begin to graph slightly more complicated stuff. So we're going to have y is equal to modifier of 3. This is going to be sine function. It's going to be x, default x with an invisible coefficient of 1. So we're not doing anything quite too funky just yet. So this is standard period. We're going to have minus 1 pi over 2. And then we're going to have a shift upwards of 1 space. So we have 3 transformations. We have a translation to the right. We have a translation 1 space up. And then we have an amplitude change. So we have 3 transformations applied to our parental function, sine of x. Again, no period change. So the 4 hash marks are still standard. I'm biased more towards the right hand side, so I'll put my graph more over to the side. Standard 4 hash marks, so 1, 2, 3, 4. This is unmodified period. So full circle is the standard 2 pi. Because this x here is not getting modified by something other than 1. So standard 4 hash marks reaching 2 pi. So we can label the rest of these if you really want to. This is going to be pi. This is pi over 2. This is pi over 3 pi over 2. This is an amplitude change of 3. So let's immediately put hash mark right here. But if you just want to put 1, call it the maximum for now, 3. But we do have to shift it upwards by 1 space. So I'm going to put 4 hash marks. So 1, 2, 3, and then 4. This one I'll just call it 3. No, let's call this one 4. I'll label this one. So that's a 4. This is 1, -1, -2, -3. We probably don't need to go beyond that because, again, this is a shift upwards of 1. Alright. So let's start off by graphing the parental function, just sine of x. So if we graph just sine of x, I guess we should consider the amplitude. I like to, when I graph this prior to shifting shifting to the left or right or shifting upwards, I do like to take into consideration the amplitude change. So let's just, the way I like to do it is just this way. So take into consideration the sine function, and then we have an amplitude change of 3. So origin, original sin, if you like to use that mnemonic, start off at the origin. And then we hit a max of 3 for the first hash mark space movement. So 1 hash mark movement, and then 3 spaces upwards. That's standard movement. And then next up, moving over to the next hash mark, we're going to go hit back to 0, because we're not considering that, and we're not considering this at the moment. Just base sine function and amplitude change. So next hash mark movement over, is going to hit the minimum, which should be -1 times 3. And then once we get to the final hash mark, that's going to be the end of the period, aka the reset value. So we hit back to 0. Alright, so that is just what this portion looks like. So now, if we take into consideration this pi/2 shift and this +1 shift, well, first I need more hash marks. So let's put one more hash mark right here. So that's -pi/2. And then we'll put one more for good measure. One more for good measure. So going back to the orange graph, now let us take into consideration the first shift. It doesn't matter which order you go. You could shift upwards one space first, and then you could shift pi space to the right second, or vice versa. It doesn't matter. Just be consistent. So I'm going to do the horizontal shift. We have a shift of pi/2, which if you check the hash marks, it's going to be one hash mark space over because of the way they've been labeled. One hash mark space is pi/2. Since this is pi/2, then we shift over one hash mark space. So we have considered shift number 1, and then now let's consider shift number 2. That's just going to be +1 to all the y values, so all y values are increased by 1. And then now we should be done. Make note that this is a graphical hypothesis. It predicts this particular point. Try not to test nodes, because nodes could lead us astray. It's honestly better to test the peaks or the troughs if you want to test your graphical hypothesis. So this one, that one's going to be pi, 4. So this point is predicted by our graphical hypothesis. So if we plug in pi, will we truly get a 4? So let's test that out real quick. This one simplifies into pi/2. Sine of pi/2 is interquadrant angle, that's +1. +1 times 3 is going to give us 3, and then 3 plus 1 is indeed 4. So this graphical hypothesis, it's probably good. Now that we've acknowledged it's probably good, we should probably continue on the graph. So this one might be a little more complicated now that it's shifted over, but just keep track of the movements. This is one hash mark space, which is going to be pi/2. So if we move one space over, since this is the maximum, then we should be transitioning to the minimum. Now if we move hash mark spaces, we have an amplitude movement of 3. So instead of moving one hash mark space over and moving down 1, we move down 3 spaces. So it's one hash mark to the left, and then 1, 2, 3 spaces downwards, so we should end up right there. Since this is concave down motif, this one's going to be concave up motif. Connect that as smoothly as possible. So there it is, and then we can continue on the concave up motif if we do one more hash mark movement over, but don't move to 0. Please don't move to 0, because this is now the shifted graph. This is not parental graph anymore, so we need to hit 0 plus 1. So this is where the nodes have been moved. So stay consistent. This one hits the new minimum, not the old minimum, and this one hits the new node. That's not located at y0 anymore. It's located one space above it, so right there. So once you've done the shift, make sure you stay consistent. That's why I like to do the amplitude change prior to the shifts. And the same is going to be true for the reflections. I always like to do reflections first, because if you do reflections afterwards, some people reflect it across the x-axis, which is incorrect. It should be reflected across the node, the axis containing the nodes. So anyway, just for future reference, that's going to be the axis of reflection. Once you have shifted this axis of reflection, and then you do your reflections, you have to reflect it across this one. But more on that another time. If you wish to continue on the graph, the next one up should be up to max 4. So up here for the next hash mark. Right here, we're transitioning upwards from the minimum. We should hit maximum at 4 for the next hash mark. So like that. So if we frame this one, it looks something a lot cleaner. So there it is. That's going to be the graph of our particular function. And we should be good to go. Just to reiterate, in my opinion, this one isn't so bad. So let's do another one, just with sine functions for now. Because again, once you know sine functions, you know cosine functions. Because cosine function is just a shifted version of the sine. So not too much to memorize. Alright, let's do another one. Let us do 1/3. No, let's not do 1/3. Let's do 1/2. This is going to be sine function. We're going to have a standard x, and then we're going to have plus 3 pi over 2. And then we'll have a shift downwards of 2 spaces. You know, let's do 4 spaces. So let's put the graph x-axis first. This is my preference. And since we have a shift downwards, and since we have amplitude change of 1/2, I'm going to bias my graph more downwards. So like this. So I'll put more in the down. Or maybe I have to exaggerate it even more. So this is going to be 1 hash mark, 1 space. Yeah, let's follow reasonable procedures. Let's do the 4 hash marks for the base sine of x function first. So 1, 2, 3, and then 4. This is an unmodified x, so it has invisible 1, so it follows standard period. Full reset. It's going to be 2 pi. You can label these ones, but I'm going to choose to not do them. And then this is going to be a minus 4 downwards. So this is going to be 1/2. So we need to hit or get close to -4. So this is -1. That's -1. This is -2. This is -3. And this is -4. Alright. And I should put some up above. +1, +2, +3. And put some in the back as well. So this is going to be -pi/2. That's going to be -pi, -3pi/2. So again, if we just consider just the base function with the amplitude change, then we start off at the origin. Sine of 0 is 0, because 0 times 1/2 is still 0. And then hash mark space over, we hit the first hash mark. Then we go to the amplitude, which is just to be 1/2. This is 1. We don't want 1. The amplitude change is 1/2. So 1 times 1/2 is half the hash mark. So unfortunately, this is going to be very tiny, but it's concave down. So I should have adjusted my axes. It looks a little bad. And then 1 hash mark over, we're going to hit 0. Next hash mark over, we're going to hit minimum, which is not -1, but instead -1/2. It's the minimum. And then on the 2 pi, the 4th hash mark, we hit reset value. There we are. So we can do the same thing on this side. We're starting from we're transitioning from the maximum, we're moving to the left, so we should hit the minimum on the first hash mark space over. And be sure to keep track the minimum is -1/2. So right here. Not -1. -1/2. And then for the next hash mark over, we should hit 0. And then next hash mark over, we're going to transition to maximum, which is not +1, it's +1 times 1/2. So there you are. As you can see, a very compressed graph. So let's put a few more hash marks right here. That's going to be one more, and then one more. So starting from the minimum, we transition to the max, which is at 1/2. Transition to 0 right there. So that's the unshifted. We've just taken into account the sine base function, sine of x, and the amplitude change. Now let us consider 3 pi over 2 shift, and remember opposite land inside parentheticals, so we move 3 pi over 2 spaces to the left. Let's put an anchoring point just to keep track. You can put the nodes, but I always recommend the maxes or the minimums for shifts. So this is at 1/2. We're going to shift it 3 pi over 2 to the left. How many hash mark spaces? Each hash mark is default pi over 2. So this one requires a 3 hash mark count shift. So let's do it. Keep track of the anchoring point. We're going to move it 3 hash marks over to the left. So that's 1 hash mark, 2 hash marks, 3 hash marks to the left. Unfortunately, this is hand drawn, so things aren't perfectly in alignment, unfortunately. Well, try our best. So something like this. It's not the best looking graph. I'm going to fudge it just a little bit. No, that's bad. I can't correct this. Well, I just have to erase it and just fill it out. Make it look a little better. So we should hit 0, and then we should hit this one. This max is at 1/2. Okay. So we've taken into account the horizontal shift to the left by 3 hash mark spaces, and now we have to shift 4 spaces downwards. So we're going to take this entire thing, keep track of the anchoring, the red point, which is currently at 1/2. So when we shift downwards 4 spaces, we're moving by hash marks, but we're between the hash marks, if you know what I mean. So fun times. So if you want to make this the new hash mark anchor point, we can. So that's currently at -1/2 prior to the shift. So we're going to take that -1/2, we're going to move it 4 spaces downwards. So this is 1 space downwards, 2, 3, and then 4, right there. Alright. That's going to be the new location, the final shift. So we've taken into account this -4 shift. So this point right here, or actually this one is easier to check. This one here is currently located at 0, and then the y output should be -4.5, or 4.5, or 9/2. So according to our graphical hypothesis, if we input a 0, we're supposed to get out a -9/2. Is it going to be true? And we'll just test it out. So 0 plus 3 pi over 2 is going to be 3 pi over 2. Sine of 3 pi over 2 is going to be interquadrant angle downwards, so it's going to be -1. And then -1 times 1/2 is -1/2. So -1/2 minus 4, that's the 4, is indeed -9/2. So the graphical hypothesis is pretty good. Again, never test the nodes. Test the minimums or the maximums, the trowels or the peaks. This one seems to be good, so this graph should be good. This one's leaking off. It's leaking off the graph. So I'm going to steal this motif. I'm going to take it and just plop it over right here. So yeah, it's going to fudge. It's kind of fuzzy right here, but you know. It is what it is. So this is going to be the minimum. So if we count 4 spaces over, 1, 2, 3, 4, this one should be a minimum. Not perfect. So this is going to be a maximum. We count 4 spaces. 1, 2, 3, 4. This one should also be a maximum. At -3.5. Yeah, something like this. Again, kind of fuzzy, but such is the nature of drawing this by hand, including the axes. Let's frame this so it looks nice. And then we should be good to go for this particular graph. Good to go. And now let us talk about the reflections, because, you know, that was inevitable. So suppose we have y is equal to negative sine of x. This one should feel familiar because the rules are pretty much exactly the same thing. So if you have y is equal to negative x squared, that's just going to be a reflection of your parabola graph downwards. So for this one, rather than your graph going upwards like so, all the y values are flipped, so it's downwards like this. Fun times. And then like your log functions, if you have y is equal to log of x, log base 2 of x, for example, all that does is reflect that as well. So if we discount this negative, the log function looks something like this, right? The vertical asymptote. But once you put the negative in front, then all it does is it just flips it. It just flips it across the axis of reflection. So instead of being like that, it's going to be like this. So reflection across this sort of horizontal bar right here. So I'm mentioning that because we pretty much have the same rule for this one. So let's do the default one first. 1, 2, 3, 4 hash marks for the parental, and then we start off the origin. It's the max, 0, minimum, 0. There it is. But once we take into consideration this negative, your graph gets flipped. So instead of being at +1, this one reflects across to -1 for the parental. From the parental. Well, 0, if you multiply 0 by negative, it's still going to be 0. This -1, however, gets flipped to the positive maximum. And 0 is still 0. So all we do is reflect the graph across the axis of rotation, which is through the nodes, which for now happens to be the x-axis. That's it. So you can imagine, therefore, what if we have a negative inside the argument? So if we have y is equal to sine of negative x, what happens to our particular graph if we have a negative inside here? And you can expect it does something familiar to what we've done before. So if you have y is equal to root x, for example, if you recall this one, if you decide to graph that one, it's just going to be this boring old thing like this. But if you have y is equal to square root of negative x, all of a sudden your domain is flipped and you're graphing this way instead. This one is that one. So we have a domain flip. All your x inputs have been reversed in a sense. And then similarly, if we have y is equal to log of negative x, for example, going back to one of our more recently graph type stuff, instead of your function looking like this again, the arguments have now been reversed. So now we're going to be headed in that direction. So not this one, but rather that one. So that's what the negative on the inside does. If you notice, there's going to be this one right here. It continues to haunt us. These ones don't show up very often. But going back to this, so that's just a reflection, and it's across the vertical axis of reflection, which in this situation happens to be the y-axis. So hence, you can expect something similar to happen in this sort of situation. If we have a negative, all it does is it reflects across our vertical axis of rotation, which again by default happens to be the y-axis, but it can get shifted. So what does that mean for us? Instead of being a forwards to the right one space up, it's forwards to the left now, but one space up. Start at 0, 0. Instead of being 2 spaces, 2 hash marks to 0, it's 2 spaces to the other side to hit 0. So instead of being 3 spaces to hit maximum, instead of 3 spaces to the right to hit maximum, it's 3 spaces, 1, 2, 3 to the left. Wait, did I say this wrong? Yeah, no, I'm sorry. I'm sorry. Instead of 3 spaces to the right to hit minimum, I was looking at the reflected graph. Let's compare it to the parental. Instead of needing to move 3 hash marks to the right to hit the minimum, we can move 3 hash mark spaces to the left to hit the minimum. So that's 1, 2, 3 hash mark spaces. And then we're hitting the minimum. So if you connect these as smoothly as possible, it's going to be starting from 0, hit maximum, second hash mark, go to 0, third hash mark, hit the minimum, and then fourth hash mark should be reset value. So all we did was we reflected our parental function, this one right here, across the axis of reflection, the vertical one, which again, in this situation, happens to be the y-axis. So be careful. That's what it's going to look like. So we already know these rules. And now all we need to do is just apply those rules. So we're going to make things a little bit more complicated now. We have, that's not the right color, whoops. We have y is equal to, we're going to have 2 minus 1/3 sine of non-reflected x minus pi. So make note of how many transformations have been applied. We have a translation to the right, that's 1. We have amplitude change, that's 2. We have a reflection, that's 3. And then we have a shift upwards by 2 spaces, that's going to be 4. So we have a grand total of 4 transformations for the situation. You can kind of bundle these together if you wish, but ultimately 4 transformations. So to begin, we just put the x-axis, y-axis. We do have a shift upwards, so I'm going to bias the graph more upwards. So I'm going to begin by laying down the 4 hash marks. 1, 2, 3, 4. I might as well put them to the left too. So we have 1, 2, 3, and 4. We have default reset value of 2 pi because this one is an unmodified x with a default 1 coefficient. So default coefficient. This is a, let's keep track of the amplitude. So how, if we put down the hash mark, what should we make this hash mark? It's going to be 1/3. But, because we have a shift 2, I'm going to adjust my shifting. I'm going to put 2 hash marks. This is going to be 1. Not perfectly to scale. And this is going to be 2. 1 hash mark, that's going to be -1. Okay. So if we were to graph this so far, just taking into consideration amplitude, sine of x, just these. And then we'll consider the reflection, and then we'll consider the shift and the shift later. So first, just this part right here. So in consideration, sine begins at the origin, so 0, 0, original sin, and then we have the 1/3 amplitude. So when we go 1 hash mark over, we hit the maximum, which happens to be, before reflection, positive 1/3. So count. This is 1/3, this is 2/3, this is 3/3, or 1. We're hitting 1/3 for the max. So right there, 1 hash mark over. 2 hash marks over, we go back to 0. 3 hash marks over, we hit the minimum, which is going to be 1/3 times -1. So -3rd hash mark right there. And then for the 4th movement over, we go back to reset. So 0, 0. Connect these as smoothly as possible. This is going to be a maximum. This is going to be a minimum. Concave up on the minimums. So there we go. This is going to be the graph of just this part. And then now we can do the other considerations, of course. So let us consider no, I should have done this on a different layer. Whoops. That's okay. Let me undo this. So let's speedrun this part again. 0, 0. Let me put the hash marks. This is 1/3. I'm going to put them tinier than these ones. That's 1/3. That's positive 2/3. This is -1/3. This is -2/3. Good sign begins at 0, 0, 0. Hit the maximum at 1/3 for the first hash mark. Go back to 0 for the second hash mark. For the third hash mark movement, hit the minimum. Fourth hash mark is reset. It's right there. So now let's take into consideration this reflection. So we have a negative right here. I consider that before the shift left, right, and the shift upwards, downwards. So just the negative first. The axis of rotation is currently piercing through the nodes, which happens to be the x-axis. So considering this, instead of maximum, it hits minimum. Instead of minimum, it hits maximum. 0 is still 0, 0 is still 0, and 0 is still 0. Alright. So that's just considering this one, and now just the base amplitude of 1/3 times sine of x. So now let us take into consideration the shift of pi spaces. How many spaces? Since it's negative, opposite land is shifting to the right. Since each hash mark is just pi over 2, then we need to shift 2 hash marks, because 2 hash marks takes us to a pi movement. So we're going to take the entire graph, and we're going to move everything over 2 spaces to the right, 2 hash mark spaces. So this is going to be shift of pi over 2, and now shift of pi. Again, unfortunately not perfectly to scale, but kind of reasonable. So we've taken into account this shift to the right by 2 hash mark spaces. We've already taken into account this one, so now we just need to plus 2. So a vertical shift upwards of 2 spaces, keeping track of the nodes. So the node here is at second hash mark, and we're now going to move it 2 spaces upwards. Starts off at 0. So this is going to be distance of 1, distance of 2. This is the node. It should hit this one, and it should still remain on this one. I don't like to test nodes. This point right here is the one I'm going to test. It should hit this particular hash mark, and it should hit 1/3 below 2. So what is this point? This point here is going to be 3 hash marks over, which is going to be 3 pi over 2. And the predicted value is 1/3 less than 2, so that's going to be 6 minus 1 is 5, so that's going to be, wait, is that correct? Yeah, 5 over 3. Our graphical hypothesis predicts 5 over 3. And let's just test that real quick. If we plug in 3 pi over 2, we should get out 5/3. So subtracting those two, we're going to get pi over 2. So sine of pi over 2 is positive 1, and then positive 1 times this one is negative 1/3, and then 2 minus 1/3 is indeed 5/3. So graphical hypothesis seems pretty good, seems legit. And let us carry this out. I extend this out. So again, starting from this one to the next hash mark over, we should hit the maximum, which is 1/3 above the 2. So that's 1/3 above the 2. If you want to be careful, which you probably should. So next minimum should hit the node, which is right there, and then we hit the minimum for the next one. And then we can just copy paste this, honestly. So you notice that I'm grabbing it from the minimum because I want to line it up with this current minimum to the left. So the minimum should continue from the minimum because of the periodicity of the trig function. So there it is. It looks decent enough in my opinion. And then we could just truncate this one. We can put the framing just to beautify it. Nothing really interesting is happening on the bottom, so we can hit it off. We can cut this off right here. And on the viewing window, you can make it look very nice like this. That's how we graph it. With one type of reflection. Let us get to the other reflections, of course. So now we're dealing with y is equal to. We're going to have, let's just do one reflection first. So we're going to have amplitude change 3. We have sine function. It's going to be pi over 2 minus x. And we have a shift upwards of 1 space. Here's the x-axis. We have an amplitude of 3. Everything's moving up 1 space. I'm going to bias my graph a little bit upwards. Not too much, because the amplitude is 3 after all. Alright, so we should be hitting a minimum of -2. 4 hash marks over, so 1, 2, 3, and then 4. You know what, let me be extra careful. So here's how I'm going to be extra careful. I'm just going to take this copy and then I'm going to paste it. And that's how we force them to be evenly spaced. Three hash marks, 4 hash marks. Again, I like 4 hash marks because we have 4 interquadrant angles. We have a default x. Just kidding, it's reflected, but at least it's still a value of 1, -1 for the coefficient. So this one is still going to be standard 2 pi. And of course, I'm going to put the 4 hash marks to the left. So that's 1. It's 2. 3, and then 4. This is just my preference. I just like 4 hash marks. It's easy to keep track of reset values. We do have an amplitude of 3, and then so the maximum for just this portion will be maximum of 1 from the function times 3 gives us a maximum of 3, and then 3 plus 1 is 4. So we should put 4 hash marks upwards. So 1 hash mark. I'm gonna, just for consistency, I'm going to copy paste this one. So 1. 2 hash marks. 3 hash marks, and then 4. I'm gonna put 1 more because I like to have 5. And then we just need to put 3 hash marks, but technically just 2 hash marks going down. That's 1, 2. But I like a little extra space, so I'll put 1 more hash mark going down. It's not totally necessary, of course. Alright. And then just to label this just a little bit, so 1, 2, 3, 4, 5. And this is negative 3. So let's get to graphing the base of sine function. Unfortunately, it looks a little funky, but we're considering 3 times sine of just x. Not counting this one just yet. So start at the origin for the sine function. So from the origin, we should hit maximum, which happens to be 3. So each hash mark is 1 space, so we need to hit 3 for the first movement. So first movement should take us to 3 output right there. So here-ish. Something like that. And then for the next hash mark movement, hit the 0. And then third movement over, hit the negative 3. And then fourth movement is back to reset value, so 0. Hence the period of the function is 2 pi. Alright, so let us consider now this negative situation. So what does the negative do? So unfortunately, there's something you should always get into the habit of doing. You should factor out whatever number is in front of the x. You need to factor it out to make the coefficient the default 1. So what I mean by that, slap on the old parentheses and factor out negative 1. So it becomes negative 1 times positive 1x. That's default. And then this sign also changes, so it's now negative pi over 2. So this one is the true horizontal shift, not positive pi over 2. It's negative pi over 2. So the true shift is pi over space. The true shift is pi over 2 to the right, not to the left, which some people will get fooled in if they don't factor it out. So this is what's happening inside the sine function. Alright. So considering this negative, all we have to do is just reverse the whole input situation. So rather than doing 1 hash mark over to hit the maximum, we're moving 1 space to the left to hit the maximum. You know, just mirror this across. So instead of being concave that way, concave downwards that way. So instead of 2 spaces to hit 0, it's going to be 2 spaces. Instead of two spaces to the right to hit 0, it's 2 spaces to the left to hit 0. Instead of 3 spaces to hit minimum, instead of 3 spaces to the right to hit minimum, it's 3 spaces to the left to hit minimum. So instead of 4 spaces to the right to hit reset, for the purposes of graphing, it's 4 spaces to the left to hit reset. But just bear in mind that this is a periodic situation, so that's what I mean by when I'm saying for the graphing purposes. So here we have it. We've taken into consideration the reflection. So far we've taken into account the amplitude change. That's from first hash mark to 3 spaces upwards. So we're good. This is the sine function, so we passed through the origin initially. This is a negative 1, so that's a reflection. We've already done that. So we have only 2 things left. We have the true shift of pi over space to the right, and then 1 shift upwards. So let me delete the orange part. And since it's easier to continue the graph here, because I'm working in the digital medium, 1 space will take us to the minimum, because we're transitioning from max to min. This is going to be 0, 2 spaces to 0, and then 3 spaces to hit maximum. So, so I'm just kind of lining things up. Good enough. And then we hit the 0 next. There it is. So, considering the shift of pi over 2, how many hash marks is that? Well, each hash mark is still pi over 2. So we're going to take this entire thing, pay attention to any of the nodes. Let's pay in particular attention to this one. So we're going to move everything over one hash mark to the right, because we have a true shift of pi over 2. So just one hash mark over, everything should still line up perfectly. So we have considered the shift of pi over 2 to the right. Now we just need to account for the +1 shift upwards. So let us do that. So anchoring point is currently at 3. Move it everything one space upwards. And then we're done. So we just finished this one, and now this one. And here we go. This one should be right here. So this one is a point that we can test our hypothesis, our graphical hypothesis. It's currently located at 0, 4. You should not test the nodes. Be careful, because nodes could give you the wrong idea. Because if your graph is reflected, and then you checked out the nodes will be consistent, but the min-maxes will not be consistent. So a slightly better discriminating plug-in test is to plug in the minimums or the maximums. Don't plug in the nodes. Alright. So again, if we plug in 0 for x, we should get an output of 4. So plug in 0 for x. 0 minus 1/2. I'm sorry, 1/2. 0 minus pi over 2 is negative pi over 2. That makes it positive pi over 2. And sine of positive pi over 2 is just interquadrant angle, which takes us to 1. And then 1 times 3 will give us to 3. And then 3 plus 1 takes us to 4. Is that what our graph predicted? Yes, it is. So this point is consistent. So it looks like it's going to be a good graph. And let's just frame this one. I'm just going to cut this part off. Perks of the digital medium. I'm going to cut it off right here. And we'll cut it off like right here. Cut it off like right here. And the graph looks good. Alright. Good to go. Which means we just need to address one more thing for the sine function. It's going to be the period change, everyone's favorite. So now we're going to have y is equal to sine of something like 2x, for example. So what does this exactly do to our function? Well, basically it just means that we're now twice as fast in hitting our reset value. Because if we compare it to the parental function, sine of x, in order to hit standard reset value, the periodicity for this one is 4 hash marks over to 2 pi. So 1, 2, 3, and 4. This is 2 pi for the parental function consideration. So we start at 0, 0, hit max, 0, hit minimum, reset value. It takes a total of 2 pi, because if you plug in 2 pi directly, then we reach 2 pi. However, for this function here, in order to reach reset value of 2 pi, we don't put 2 pi into here anymore, because we have a modifier of times 2. We're twice as fast. So what that means is you only need to put in just a regular pi, because if you put just pi, it's going to be multiplied by 2, which takes us to reset value. So again, we're twice as fast because of this modification. You could think about it like working a job. Like suppose you earn $20 an hour, right? Let's consider for a moment. Consider for a moment like something like a linear function. So if your job is $20 per hour, then in order to earn $20, the first hour prior to tax will take you to $20. There it is. So if you work 0 hours, you get nothing. If you work 1 full hour, then you theoretically have $20 prior to tax. So if you work 2 hours, then you theoretically have $40 before tax. So that's just going to be y is equal to 20 x. If, however, you now have a special modification, you're now earning double of what you earned. You're now earning $40 per hour. What has happened, right? So essentially what has happened is you're now doubling your old situation. Your old situation was $20 per hour. And now we're doubling it. So what that means is you're earning twice as fast. And by extension, you only need to work half as long to reach what you would have earned before. So for the base function, it would have taken you 2 hours to earn $40. But now, considering this doubly rate, you're now twice as fast in your earnings. You only need to work half as long in order to reach the same amount for $40. So what you can see happening is that your graph got kind of squished more towards the vertical. So in effect, this has been horizontally compressed. Why? You're twice as fast. So you only need half as long to reach what you were able to reach before. So again, just to reiterate, 2 hours to reach $40 for your standard situation. But if you have a bonus modification of you now earn twice as much, you only need half as long to reach the same $40 as before. So everything takes half as long. Which means, since you're twice as fast, instead of taking 4 hash marks over, which is the standard 2 pi, you only need half as long. So rather than putting the 4 hash marks like this, you can conceptualize it as just focusing 4 hash marks up to pi, because that's going to be our new reset value. So 4 hash marks, 1 hash mark, 2, 3, and 4, and that should be enough to capture our full period. So starting from 0, 0, hit maximum, hit 0, hit minimum, reset value. So the period is only going to be pi because, again, we're twice as fast instead of the standard 2 pi. So just a minor point, just to be careful. Full reset for the trig function as a whole is this whole thing still needs to be 2 pi. But because our modifier is going to be 2, we just happen to reach 2 pi a lot faster. So there's a subtle distinction that I just want to point out right there. So you can imagine what happens if you have a different modifier. Let's say we have 1/4 instead, right? So we're talking about something like y is equal to sine of, in parentheses, 1/4 of the x. So we're now 1/4 as fast as what we try to put in. So if you try to put in the full reset of 2 pi for standard parental function, it gets cut by 1/4 into 1/4. So this one will be insufficient for hitting reset value because it's modified by this 1/4. So essentially what this means is we're now 4 times slower. We're 1/4 of the speed. So it takes us a lot longer to hit reset value. So what that means is we need to hit 4 of these. So 1, 2, 3, 4. So we hit reset value. What is the value of that? At 8 pi. Because 8 pi, if that's your input, it's going to get hit by that times 1/4. 8 over pi times 1/4 takes us to 2 pi, which is true reset. So it's going to take this long to hit reset. So let's graph that real quick. So that is going to be, it's kind of hard to keep track. This is going to be pi, 2 pi. This is going to be 4 pi. This is going to be 6 pi. And this is 8 pi. So it takes us to 2 pi to hit the maximum. So this is one big movement. So it hits from 0, 0, start off default, hit maximum. It takes us this long to hit the 0. It takes us that long to hit minimum. And then this long to hit reset value. So this is the full period for the modified situation of 1/4 modifier. Because again, we're 4 times slower. We're 1/4 of the speed is what we had before. So that's referred to as the, what is that called? The horizontal expansion, or whatever you want to call it. So it depends on teachers. Some teachers call it something else. So whatever vocabulary your teacher uses, please use that one. I'll just show you how I generally graph these ones. It's not too bad, honestly. Okay. So suppose we have something like y is equal to sine in parentheses 3x, right? So this one we're 3 times as fast. But the way I like to graph it, I still put 4 hash marks. I'm always biased more towards the right, so like this. I just like to put 4 hash marks. So 1, 2, 3, 4, because that's how I keep track of my full cycles. Just 4 hash marks first. But we know that this is a modified thing. So this 4th hash mark, it ain't going to be 2 pi. Not anymore, because we have this 3 times as fast. So the question is, what will it be? Well, for default full period, it's going to be 2 pi. So all you need to do is take this one, and you force it. This whole thing needs to be 2 pi. Because that's what standard reset full period is. It's just 2 pi. So if we force the inside to be equal to this one, all you need to do is solve for the x. So divide by 3, divide by 3. So x, in order to hit full reset value, is going to be 2 pi over 3. So that, from 0 to 2 pi over 3 prior to shifts, is going to be full, what's it called? Full period. So from here, 4 hash marks is full period. We've just determined that 2 pi over 3 is the full period. So how do we populate the rest of these hash marks? That's not too bad, actually. You just take this one, divide it by 2, and that'll take you to this hash mark. So if you divide by 2, you're essentially multiplying by 1/2. Half cancels with this one. So it means that this second hash mark is just pi over 3. To get this hash mark, just divide this by 2. What's this one divided by 2? It's pi over 6. What's this awkward third hash mark? It's just going to be this second hash mark plus the first one. 1 hash mark movement is pi over 6. So to go from here to there, you just add pi over 6. So that's 3 pi over 6, which is pi over 2. So we have successfully labeled the 4 hash mark standard movements. So that's why I like 4 hash mark, because it's still going to be 4 hash mark spaces, because this is no longer 2 pi. All right. Amplitude is default 1, so this is just going to be 1 and negative 1. So let's get to graphing this nonsense. This is sine, it's unshifted. We're just having this portion right here. Amplitude is just 1. Start off at 0, 0. First hash mark. That's why I like to do just hash mark movements. So it's 1 space over, 1 space up, because it's to 1. 2 hash marks over to hit 0. 3 hash marks over to hit minimum. 4 hash marks for the full reset back to 0. So we have concave down, and then we have concave up. And then that's it. Of course, if you want to do a little bit more, we can. We have 1 hash mark over. That's just negative pi over 6. And then you continue as such. So this is transitioning from max to minimum. So something like this. And then you just frame this very nicely by cutting off, truncating the view. this is kind of bad form, so let's do this one. Okay. And that's going to be it for this particular function. Should be good to go. Let's do another one. Y is equal to sine of, let's say, 1/5. So now we have this nonsense. We're now 5 times slower because we're now at a 1/5 of standard speed. So our graph is going to be horizontally stretched because now everything takes a lot longer to hit reset. But what is the reset value? So we want the entire argument to be equal to standard reset value, which is 2 pi. So all you need to do is solve for x. So times 5 times 5. X is equal to 10 pi. So now it takes from 0 to 10 pi unshifted to reach full reset. This is referred to as the period. The period is going to be 10 pi, which we got from this setup. So the way I like to graph it is, again, I just like to put 4 hash marks so it doesn't stretch my graph ridiculously. So count 4 hash marks: 1, 2, 3, and then 4. I'm going to put 1 hash mark to the left. This is default amplitude of 1, so this is going to be 1. Technically it's supposed to be really, really low, but I'm going to put it not to scale, positive 1 right there, and negative 1 right there. Alright. So this is just sine function. There's no shift left or right, or nor up or down. So starting with 0, 0. First hash mark over. Well, let's label the hash marks first, before we get too excited. So it takes 10 pi to reach full resets from 0, 0, 0. So this 4th hash mark is going to be pi over 10. I'm sorry, 10 pi. What am I saying? Pi over 10. So to label this one, that's halfways to 10. Halfways is 5. Halfways of 5 is 5 pi over 2. Just add this one plus this one to take you to this one. So that's 15 pi over 2, I believe. Yeah. 4 hash marks have been labeled. Amplitudes have been labeled. So let's get to graphing this situation. It's not too bad. Standard movements: 0, 0. First hash mark over, you hit max. Second hash mark, you hit 0. Third hash mark, you hit minimum. Fourth hash mark, which is 10 pi, is reset. Concave down, concave up. And then we're done. If you wish to beautify, you always can. Transitioning from max to min. Transitioning from min to max. Oh, that's a little too high. There it is. Alright, that's probably good enough. So truncating it for the viewing window purposes. I'd frame it like this. And then we're good to go for this one. Alright. So let's put it all together, because at this point I think we have all the tools we need to do a full graph. So we're going to have, I'm going to call it f of x arbitrarily. F of x is equal to 2 minus sine, let's do 3x. 3x, and we'll have minus pi. So that's going to be the function we're dealing with. We're going to have to graph this. Keep in mind how many, take a quick survey of how many transformations are being applied. We have period change. We have a fake shift because we have to factor out the 3 from both of those terms first. So let's do it. So from those two terms, factor out the 3 to get true horizontal shift. So it's x minus pi over 3. So that's true shift of pi over 3 spaces to the right. This is happening inside our base sine function. we do have a reflection, and then we have a shift upwards of 2 spaces. So I'm going to move it over to right here, because you can add in any order you wish. So this is more standard form. Let's take that into consideration. Let's do our x-axis. Let's do the y-axis. Everything shifted upwards 2 spaces, so I'm going to bias the graph upwards like this. We have a period change. This is a ×3 modifier, so let's force the standard 3x. So not counting the horizontal shift just yet. Some people like to do it at the same time, but personally, I don't. So just considering the modification of 3, not this one. Standard period is going to be 2 pi, always. Divide by 3, divide by 3. So our full reset value is going to be 2 pi over 3. So this is the period. So when I lay down the 4 hash marks, it's going to be 1, 2, 3, 4. This one, from 0 to there, unshifted, is 2 pi over 3. So to label this hash mark, that's half of this one, which is just pi over 3. To label this one, this is half of this, which is pi over 6. And then adding these two takes us to this one, which is just pi over 2. Alright. Keep in mind the amplitude change. This is just a -1 reflection, but the coefficient number is just 1. So, not to scale, +1, -1. Since we do have a shift upwards of 2 spaces, I'm going to make it up to 3. So this is 1, this is 2, this is 3. Alright. And that should be enough to get started with the graphing. So let's just consider those ones first. Just that one. So if we were to graph just this orange part, it's going to be standard origin. This is a 3. We've already considered this period change of 3 by doing the hash marks in this exact labeling. And then we have default 1. We'll consider the reflection afterwards. So from here, 1 space movement to the first hash mark takes us to max. Again, no consideration of reflections just yet. And then second space hits us to 0. Then third hash mark movement takes us to the minimum. And then fourth hash mark movement takes us back to reset value, which is 0, 0. So just to reiterate, this whole orange thing is only graphing sign, positive sign of 3x. Just this one. But we do have some few things to consider. I should have done this on a different layer. Hold on. Same strat though, we'll just put on a different layer. Alright, so this layer, again, we're just considering this one. 0, 0. Hit maximum, 0. Hit minimum, reset value. Now let us consider the reflection. This is just a negative outside of the main trig function, so this one just affects the y values. So we're going to reflect it across the node, the axis containing the nodes. So instead of being upwards right here, it's going to be downwards there. So 0, 0, because 0 times negative is still 0, but then instead of being +1, it's going to be -1 on the reflection. 0 is still 0. Instead of being -1, it's going to be reflected to +1. And reset value is still 0. So because 0 times negative, it's still 0. So we've taken into account this. We've taken into account those. And now we just need to do 2 shifts. This shift and then that shift. That's my order of preference. So let us take into consideration the first pi over 3 spaces. This is why I like labeling my hash marks first. Because in order to do a shift of pi over 3, how many hash marks is that? Well, you notice this is pi over 3. That's a shift of 2 hash mark spaces. To what direction? Opposite land, and so it's going to be to the right. 2 hash mark spaces to the right. But let me put a few more hash marks. Let's put 2 hash marks over, so 1 and 2. Alright, so I'm going to extend this graph just a little bit prior to the shift. It's max transitioning to minimum. So it's going to be 0 right here, and then reset is there. Minimum transitioning to maximum, so this one is going to be max. Unfortunately, hash mark isn't exactly to scale. Good enough. Alright, so again, considering the pi over 3 shift to the right, that's 2 hash marks. I'm going to arbitrarily set this one as the anchor point. And it's not perfectly to scale. It's supposed to be here-ish. So everything 2 hash marks to the right. So anchor point, 1 space, hash mark, 2 hash marks. Alright. That part is done. I'm going to extend the graph just a little bit just to beautify it. So this is 0. We're hitting 0 on the max. And then we hit minimum. This is supposed to be more over. Let me just move it just a little bit. It's kind of bothering me. There-ish. Wait, not -1, I'm sorry. Hash mark is, 1 hash mark is pi over 6, so this is negative pi over 6. Okay, so we've considered the shift 2 spaces to the right, and then now we just need 2 spaces upwards because of the way the hash marks have been defined. Because I like thinking about it in terms of just movements, strictly movements. So we're going to take this one. The anchor point is currently at 1. We need to move it up to 1, 2. And that's the best I can do for the situation. I'm going to delete this because I'm going to cut it off there. So we have the anchoring point here. It's supposed to be there and there. So this point, this graphical hypothesis predicts this particular point, which is pi over 6, 3. So if we plug it in, it should work out. Let's check it. So if we put pi over 6, we're supposed to get an output of 3. That's in consideration. So this one minus that one is going to give us negative pi over 6. Negative pi over 6 times 3 is negative pi over 2. Sine of negative pi over 2, that's going to be downwards interquadrant angle, which is -1. Modified by -1 is +1, and then +1 plus 2 is +3. So that checks out. So this graphical hypothesis is probably good. Let's just frame this properly to make it beautiful. Just like me. And now it's like this. And we should be good to go. And thus have we successfully graphed this particular function. We should be good to go. Wonderful. And as I mentioned, all things have been considered. We've considered the shift upwards, downwards, shift leftwards, rightwards. We've considered the reflections, reflecting across the horizontal and then reflecting across the vertical. And then now we've considered the period changes. That pretty much takes care of the entire graphing for sine functions. Let's just talk about the cosine function in brief. It's going to be the same thing. Whoops. Or almost the same thing, because this one is just a shifted version of the sine function, honestly. And just to make this more explicitly like an argument, I'm going to put parentheticals. So when we graph this one, Same situation. We have the x-axis, we have the y-axis. I just like to put 4 hash marks. 1, 2, 3, and 4. This is unmodified x, so it's default 2 pi. Half of that is pi. Half of that, pi over 2. This one plus this one takes us to 3 pi over 2. There is an invisible default amplitude of 1, so we have upwards of 1, and then downwards of -1. And now we just got to graph this one. But instead of starting at the origin, because sine starts at the origin, again, this little mnemonic might help you out. Original sin, sine starts at the origin. This is cosine, unfortunately. It starts off at a very awkward 1. So why does it start at 1? Well, it takes us back to the reference triangle. So back to another graph. To understand this graph, you go to this one, right? So inner quadrant angle 0 is right here. So when you take cosine of 0, that's the collapsed triangle. That's when the opposite is 0, but the adjacent matches the magnitude of the hypotenuse. So it's a 1-to-1 ratio. And since this is in the positive x direction, it's positive 1-to-1. So cosine of this quote-unquote collapsed triangle is positive 1. And this collapsed triangle, the angle of it is 0. That's why we're right there. And we can continue plotting points if you wish. This is another interquadrant angle. Cosine of this interquadrant angle. This is the collapsed triangle pointing upwards. This one quote unquote has no adjacent, so the adjacent is 0, but the hypotenuse still exists. So 0 over non-0 is 0. So hence 0. And then cosine of this interquadrant angle, if you do it, it's going to give you -1. Cosine of this next interquadrant angle, that's the collapsed one pointing downwards. It has no adjacent, so 0. Reset value takes us back to 1. So how do we connect this? Don't do this. It's not a linear function. Because if you graph pi over 4, it doesn't give you 1/2. It gives you above 1/2. So here-ish. So you can't continue straight down. It's going to be concave downwards. Hits the 0, transitions to minimum, so that's going to be concave up on the minimum. Hits the 0, this is the maximum, so it's going to be concave down on the maximum. Again, you could always plug half points, half hash marks, to verify. So there we go. That's going to be the graph of the cosine function in default position. As a comparison, if we compared it with the y function, with the y is equal to sine function, sine of x. Sine original sin, if you like that mnemonic, starts off there, hit the maximum, hit 0, 3 hash marks over, hit the minimum, reset value, go back to 0. As you see, if we take this one and we move it 1 hash mark over to the left, if I draw this better, it should be a perfect overlap, but I couldn't draw it not perfectly, but there it is. So if you shift it over, so what that tells us, that how do we shift it over pi over 2 spaces to the right? Well, to shift to the left, I mean, it's going to be plus pi over 2. So if we add pi over 2 to the x inside our sine function, then this is a shift 1 hash mark over, which shifting 1 hash mark over, it will take us to this position. So if this had been drawn correctly, you know, because hand drawing leads to funkiness, it should match perfectly. Which leads us to one of the properties of sines and cosines. You could just transform one into the other one by adding or subtracting pi over 2. but that's for default. Obviously, if you have transformations, then you need to have different pluses or minuses, at least on visual inspection. But in essence, it's just pi over 2 shift. Because ultimately, those two trig functions are related inside a right triangle from a certain point of view. Because this is one angle and this is another angle. Depending on which angle you look at, opposite can become adjacent and vice versa. Okay. That's just a minor thing to talk about, though. Of course, this is not the only shift that we can get. I think the more popular form for this one is going to be this other shift. This is going to be the more popular example. This is 90 degrees because it's complementary angles, minus this one will take you to that one. So we'll talk about that one probably another time. But I just wanted to talk about the comparison between these two. So again, exact same movements. It's not too exciting in my opinion. So that's why I more heavily emphasize the sine function rather than the cosine. But once you know one, you know the other one. And all the prior rules that we've talked about still apply. So we're talking about left-right shifts, up-down shifts, amplitude changes, reflections, they're all the same. Period changes are all the same. So let's get to graphing cosine stuff. So we'll call this function g of x. G of x is equal to, let's do something kind of mildly annoying. Let's do 1/3 minus 1/2. Let's make things miserable. And then we have cosine. Cosine of what? Let's do pi minus, note the two reflections. Minus what? Let's just do 2 pi. 2x, I mean. And that's pretty much all the transformations you have to worry about for the most part. But they're all loaded up in this particular problem. We have a reflection number 1. We have a reflection number 2. But this one's across the vertical and this one's across the horizontal. We have a period change of 2. We have a shift. This is not the true shift, bear in mind. We need to factor out the -2 from those. So factor out -2 from those two terms. We're getting -2 times positive 1x. That's what you want. Minus pi over 2. And this is our true horizontal shift. This is inside the cosine function. We do have an amplitude change, 1/2. We have the reflection. We have a positive 1/3 shift upwards. And again, you could add in any order you wish. So that's what we're working with. I'm going to take this one and just plop it right down. Right there. It's not too bad. Just have some regular procedures. X-axis is here. We do have a awkward 1/3 shift upwards. We do have a amplitude change. So everything's kind of squished. So I'm going to emphasize this slightly upwards, like so. We do have very awkward increments. So to consider that, common denominator to 1/3 and 1/2 is going to be 6. So I'm going to break everything down into sixths. So this is going to be positive 1. And here's where the magic happens. Just count 6 spaces upwards, right? So 1. This is going to be kind of annoying, actually. This is going to be half space. So 2 spaces and then 2 spaces. So 1, 2, 3, 4, 5, 6. That's 6 out of 6. So each hash mark space is 1/6. But the big hash mark is positive 1. So keep that in mind. So that one right there is, what is that? -3 over 6. So that's -1/2. And for any trig functions, for sines or cosines, I always like to put 4 hash marks. So counting up 1, 2, 3, 4. just for slightly more accuracies, because there are going to be a lot of shifts. So this one I'm going to try to be very consistent. So hence the required regularity in the spacing. So that's 4 hash marks. I'm going to put 1 more for good measure. Alright, let's put 2 more for good measure. But I'm focused on the 4 hash marks first. So just these 4 right here. What is true reset value? It's not going to be the standard 2 pi. Why not? Because we have this 2 modifier. So take the 2x. I'm ignoring the negative. I'm ignoring the shift. We're going to force it to be standard 2 pi. So solving for x is equal to pi. So this is the period, which means from peak to peak, that total distance is going to be pi. That is confirmed. But I also use this to double up. So discounting any shifts, we start off at 0, 0. We're going to hit up. We're going to hit down. We're going to hit reset. This reset is going to be at pi. Again, prior to shifts. So let's get to graphing this main thing right here. Not counting the shifts just yet, but we will count the reflections, of course. So reflection we will consider. Reflection we will consider. But we are first considering just cosine of 2x. I might as well do the amplitude. So considering amplitude, cosine, and the 2x. So we're going to start at not 0, 0, because that's the sine function. So rather than that, we're going to start off at the max value, which is positive 1/2, which is right here. First hash mark movement, we're going to hit 0. Second hash mark movement, we're going to hit minimum, which is again negative 1/2. Prior to reflection. 3 hash mark spaces over, we hit 0. 4 hash marks, we hit reset value, which is right here. But what is that 4th hash mark? It's pi. Just pi. I was going to say pi over 2, but it's just pi. So reset prior to shift is pi. Half of pi right here is pi over 2. Half of this is pi over 4. This one plus this one takes us to this one. 3 pi over 4. Alright. So now we just connect these as smoothly as possible. Halfways of this one should take us above half. So it's concave down. Concave up on the minimums. Concave down on the maximums. And I'm just going to continue this onwards just a little bit, and just a little bit. I should put some hash marks to the left. Just a few, just a couple. That's 1 hash mark, and then I'll be 2 hash marks. Okay. Good enough. So this is going to be concave down. Make sure you hit the reset right, 0 right here. The minimum. As you notice, great regularity with this graph. Periodic. Alright, so we've successfully considered the amplitude. We've successfully considered the cosine function. We've successfully considered the period change. Now let's consider the reflection number 1 and the reflection number 2. You can go in any order you wish. I'll just do this one arbitrarily. So we do have the negative consideration first. Right here, all that does is it affects our inputs. So our inputs are reflected. Does that really do very much? Not really, because this one right here gets reflected to right there. This negative 1 gets reflected to right there. This positive, I'm sorry, no, I said 1. but this is an amplitude change. This 0 gets reflected to this 0. This negative 1/2 gets reflected to there. This positive 1/2 gets reflected to right there. So in essence, this negative here doesn't really do anything. So this is technically accounted for. Now we have a negative reflection across the node axis. This is where the node is located, which happens to be the x-axis. So everything gets reflected across. So what happens? Instead of being positive 1, it becomes negative 1. A negative 1. Instead of being positive 1/2, I'm sorry. That's positive 1/2. It ends up being negative 1/2. All the zeros remain the same thing prior to shift. So just copy the nodes. Instead of being positive 1/2, it's negative 1/2. So instead of being negative 1/2, it's positive 1/2. Instead of being negative 1/2, it's positive 1/2. So let's connect them as smoothly as possible. Concave down on the max, concave up on the min. Concave down on the max, concave up on the min. So with this red graph, we have thus considered both of the reflections. So now we just need to do the true shift and shift up. So we have a true shift of pi over 2 spaces to the right because of opposite land. So we're going to take this whole thing. Well, let's first put an anchoring point. Let's consider this for the anchor point. So we're going to take this entire graph, shift it 2 hash mark spaces to the right. So that's 1 hash mark space. Hey, that's a perfect overlap. 2 spaces to the right. And we have considered the pi over 2 spaces to the right. Now let's take this 1/3 into consideration. So you have 1/3. That's just going to be 2 hash mark spaces upwards because we broke it down into 6 divisions. So 1, 2. Unfortunately, this is hand drawn, so the anchor points are kind of botched up. That's good enough. Okay, good enough, but let's keep track of the movements. Remember, this is the anchoring point. It moved up 2 spaces, 2 hash marks. So it moved upwards from the negative 1/2 to right here, right? So in consideration, from the negative 1, it'll be plus 2 hash mark spaces, which is just going to be 1/3. So doing the simple mathematics, convert them into the same denominator. So it's negative 3 over 6 plus 2 over 6, which takes us to negative 1/6. That's currently located at hash mark pi over 2. So that point is pi over 2, comma, negative 1/6. That's our predicted point from our red graphical hypothesis. We don't need the orange one anymore. Perks of the digital medium. If you're doing this on paper pencil, it's a little more annoying. Just keep track of the nodes and the min-maxes. That's my recommendation. Alright. So, is this point consistent with the actual equation? So we're going to take pi over 2, and we expect negative 1/6. So if we input pi over 2, do we in fact get a negative 1/6? Oh, I put this in the wrong location. Whoops. It goes right there. So 2 times pi over 2 is just pi. Pi minus pi is 0. Cosine of 0 is going to give us 1. 1/2 times 1 is negative 1/2. And then lastly, 1/3 minus 1/2 is indeed negative 1/6. So, seems legit. So it means that the graph function is probably, our graphical hypothesis is probably correct. I'm going to arbitrarily cut it off right here. And right there. And we're basically done with the function. graphing the function. Again, don't test the nodes. And by nodes, I mean these ones right here. Don't test these ones right here. Because the nodes don't consider the reflection right there. So it makes for poorer tests. So test minimums or test maximums. Don't test the nodes. And we're basically done graphing the sine function. I'm sorry, the cosine function. As you see, it's the same rules, thankfully. I guess that takes us to graphing the tangent functions. Those ones are honestly way more annoying. But the ideas are mostly the same thing. But we do need to consider what the parental one looks like. So just tanks. And just to make it explicit, it's tangent of x. X is the argument. Alright, so we're going to put the x-axis and then put the y-axis. But there's something to consider, though, for the situation. If you recall one of the properties for the tangent functions, this one can be transformed into sine over cosine. So there it is, argument number 1 and then argument number 2. They're the same arguments. But before we talk about this, let's talk about an old acquaintance of ours. Y is equal to 1 over x. If you recall, this is going to be the reciprocal function, the rational expressions, graphing rational expressions. If you recall this one, we can't divide by 0. We have, for this situation, a vertical asymptote. Where is a vertical asymptote located? It's where we create 0 on the bottom. So if x is 0, we have 1 vertical asymptote. And then ignoring the horizontal asymptote for now, because it's not relevant for the trig functions. If we consider that one and we graph this, it looks something like this. And we never ever cross the vertical asymptotes. So again, why do we have this vertical asymptote where our graph cannot cross? Because we can't divide by 0. Why do I bring up not being able to divide by 0? Because this is a fraction. And we make note that there are instances in which cosine of x can be equal to 0. Considering interquadrant angles, right? So how do we, in what situations do we generate 0 on the bottom? If we hit interquadrant angles right here, upwards, or the downwards collapsed triangle. So in other words, pi over 2 increments, and negative 3 pi over 2. Or positive 3 pi over 2, I should say. So what does that mean? It means that when we first hit this one, if we consider coterminal angles, to get to the next one, it's just going to be plus pi. To get to the next one, it's pi. So plus pi k. So these situations where k is an integer will lead to the bottom becoming 0. And we can't divide by 0. Because that creates domain issues. Which means, for graphing this one, there are going to be vertical asymptotes, similar to our rational expressions. Because again, by the nature of the tangent function, it's essentially cosine of x on the bottom. And how we can generate zeros on the bottom is dictated by this thing right here, which creates zeros. Which means we have vertical asymptotes where we create zeros on the bottom. Which, in the easiest, smallest sense, pi over 2 and negative pi over 2. Because if k is an integer that's negative 1, negative pi plus pi over 2 results in negative pi over 2. Those are the closest, you'll see what I mean by closest in a moment, vertical asymptotes. So closest to this y-axis. So if you move one hash mark over, that hash mark I like to label as pi over 2. Why pi over 2? Because that's the closest vertical asymptote to the right-hand side for our tangent function, because cosine results in 0 if you input pi over 2. So vertical asymptote, one of infinite many, because cosine is cyclic, is periodic. You'll hit 0 on the bottom periodically. But again, the first positive value we encountered to the right is pi over 2. And then the first negative input that will give us a denominator of 0 is negative pi over 2 because of cosine considerations. Whoops. I just goofed that one up. And let's put the another vertical asymptote right here. And again, we have infinite vertical asymptotes because there are infinite ways to make this bottom to 0. How do we make the bottom into 0? According to this rule right there. So let's take that. So what's going to be our next positive vertical asymptote after this one, right? Well, just follow this particular formula. So if k is equal to 0, then that takes us to the first vertical asymptote. But if k is equal to integer, positive integer of 1, then pi plus pi over 2 will give us 3 pi over 2, which takes us to the next one. Oh, it's too close, I'm sorry. Right there. This is halfway's point, right there. So okay, this is another VA. So if you wish to get to the next negative one, we could just add 1. We could subtract 1 full pi from this one. Takes us to right here-ish. I don't care too much about this one, and I don't care too much about this one. I just care about the closest to this 0, 0 right here, because I love 0, 0. Everything's easy when it's 0, 0, for the most part. But again, we're still trying to graph this tangent function. All we've done is made note that we can make the denominator into 0 because tangent is ultimately a ratio between those two. And because there are zeros, we have to have vertical asymptotes. But let's graph the actual, let's start actually putting points. And one point that's very easy to do is going to be 0, 0, because we can input 0 and 0, because this one, 0 is valid within the cosine function, but then 0 for the sine function, that's inner quadrant angle right here, opposite is 0. So which means 0, 0 is a standard default point on our parental function tangent of x, which is right here. Now here's where things are a little different from the sine and cosine graphs. I just like to take halfway's point. So this is 0. This is to the wall, the vertical asymptote wall. What's halfways between here and here? It's going to be a familiar friend. What's that? It's pi over 4. That's inner quadrant angle. That's going to be special right triangle in the first quadrant. It's our classic 45, 45, 90, which is 1 to 1. Why do we care about this? Because tangent is very easy for 1 to 1. So if we input pi over 4, that takes us to first hash mark 1. So again, 1 hash mark movement, because of the way it's been defined as pi over 4, takes us to positive 1 right here. So that's nice. But how do we connect those 2 points? It's not going to be a linear function, so not like this. So it's either something like this or something like that, right? So which one is it? So at this point, if you want to be a little more robust, you can plug in something that's less than pi over 4, which is pi over 6, which should also be familiar, right? So if you plug in pi over 6, that's going to be slim angle opening up to slim side. And the ratio for this reference triangle is 1 to 2 to root 3. So the tangent of this one is going to be 1 over root 3, aka root 3 over 3. So what is root 3 over 3? It's less than, wait, what is this? Well, what's 1/2? Let's compare it. Let's compare this to 1/2 because we're trying to determine something, right? Is it going to be less than or is it going to be greater than? Well, let's first change the common denominator. So that's going to be 2 root 3 over 6 in comparison to 3 over 6. This one is square root of 9. If you multiply this back into there, it's 4 times 3, which is 12. So root 12 over 6 is indeed greater than root 9 over 6. So this one is greater than 1/2. Wait, is it? Let me make sure I did my math correctly. Yeah, top and bottom times 2. Yes. Wait, why is it so weird? Something doesn't seem quite right. Hold on. Because this is supposed to be lower. This is half. From what I remember, it's supposed to be something like this. It's supposed to be concave up. But let me make sure the math is correct. Because this one seems kind of off. So plugging in pi over 6 for tangent function, it's going to be 1 over root 3. Yeah, 1 over root 3. This is 1 over root 3 rationalized in comparison to 1/2. Is it going to be greater? That one is correct. That one should also be correct. Yeah, 3 over 6. That's square root of 9. But change this back solely into radical. This is 4 times 3, which is 12. Yeah, this should be greater. Interesting. So halfways is greater than half. It's like here-ish. That feels really weird. That doesn't seem right. But that's what the math says. So let me delete this real quick. Whoops. Well, I should have colored directly onto here, unfortunately. But it is what it is. Let me delete this part real quick. So this is the dubious point. I have a feeling it shouldn't be there, just from what I remembered. But that's what the math says. Alright, let me just test this again one more time. So this point right here is halfways of this one, right? But that's not what we're testing. We're testing pi over 6. And pi over 6 is less than pi over 4, first and foremost. Because numerators are the same, but the denominator is greater here, so the overall number is smaller than pi over 4. So that is correct. So that's not halfways. Oh, because I picked halfways. I'm sorry. Pi over 6 is... What's halfways? Pi over 8, right? So pi over 6 is greater than pi over 8, so it's somewhere between those two. It's like right here-ish. Oh, no, okay, it makes sense. It makes sense to me now. So from our prior discussion, if we expected, just as an expectation, right? If we expected this one to be 1/2, this one in comparison, since it's past halfways, is going to be greater than 1/2. So it's like right here-ish. Okay, that's fine. That's fine. So pi over 6 isn't the greatest number to pick, but if you pick another point to graph, we don't have any nice numbers anymore, right, to evaluate between here. We'd have to use our half angle properties. We're going to have to use our trig identities. but let's avoid that. So to avoid plotting those ones, well, let me say it again. We're going to avoid plotting points between here and there. So this is no man's land because we're going to have to bust out properties, which we're not particularly fond of at the moment. But I guess that would be good practice. So on your own time, you can plot points between here. But let's just use a familiar friend. If we go to limits, revisit the idea of limits. So we can't plug in pi over 2 directly into our tangent function because that's directly on the vertical asymptote. We can't divide by 0. So rather than do that, what if we plug in something that's very close to pi over 2 into our tangent function? So what is very close to pi over 2? Well, we're just going to put pi over 2. But it's going to be a value that's slightly less than pi over 2. But for our analysis, we're going to plug it into tangent equivalent, which is sine of x over cosine of x. So again, we can't plug in pi over 2 directly into this situation because that will create 0. But we can imagine, what if we plug in something very close to pi over 2? Very close to pi over 2. So if you plug in something very close to pi over 2 into our sine function, that takes us very close to 1. It's not quite 1. It's slightly below 1. But we don't care because it's a close enough to a discrete value of 1. But if we plug in pi over 2 into cosine, we get almost 0 if it's almost pi over 2. Okay? But what is cosine of close to pi over 2, right? It's going to be a triangle that's very close to the collapsed triangle. So it's going to be a positive number because we're still in quadrant 1 if we input in close to pi over 2, but less than pi over 2. Still in quadrant 1, so the result is still positive, so we get close to 0, so it's a positive almost 0. So when we get to the situation, if you recall our discussions from the rational functions, this is going to be explode into positive infinity, so positive. So if we plug in something very close to pi over 2, it takes us to an explosively high value up here. So arrow upwards to signify the limit approach. So how do we connect this point that we know is there for sure and that point there for sure? This one maybe. We just connect these as smoothly as possible. Try to connect those two. Something like this. It's not going to be a linear function. So going with this concavity, something like this. So there it is. That's how we get this one. And then how do we get this other side of the graph? Well, it's going to be a perfect reflection across this origin. It's going to look something like this. So here's how we do this. This is 1 hash mark over, which is going to be negative pi over 4. What happens with our graphing? This is negative pi over 4, right? If you consult the reference triangle, negative pi over 4 is in quadrant 4. That's negative 1 to positive 1 for the tangent. So from here to there is negative 1. So you can imagine what happens in the end behavior. So like this end behavior, we're going to have it going downwards instead. And you can verify this using the very basic idea of limits. So instead of doing almost close, instead of doing exactly negative pi over 2, we're going to go close to negative pi over 2. So if you plug in close to negative pi over 2 into our sine function, what do we get? We get close enough to negative 1. But if we plug in close to negative pi over 2 into our cosine, we get close to 0. But what kind of 0 are we looking at? Is it a positive almost 0 or is it a negative almost 0? And that is the question. Well, cosine almost 0, right? So we're not quite at negative pi over 2. We're almost negative pi over 2. But the adjacent one is still positive in quadrant 4. So this 0, this almost 0, is positive. So in consideration of this, infinity. In consideration of the sign, negative infinity. So we're going to explode downwards with the graph with a very crude limit analysis. Again, real mathematicians would scold me for my sloppiness, but that's okay. I'm not a real mathematician, so close enough. So unfortunately, the graph is a little funky, but I'll try my best right here. So something like this. So it's supposed to be smoother, so let's smooth this out. So ultimately, something like this. Oh, I know why it ended up being weird, because I biased the graph upwards. So this is supposed to be more downwards, like right here-ish. Alright, now it looks a little better. Okay. So ultimately, that's what our graph is going to look like. Obviously, that's a lot to talk about, so I'm going to summarize it by just graphing it all over again. Yeah, just to summarize. Let's talk about this again real quick. So, in consideration for the tangent function, y is equal to tangent of x. For our considerations, for graphing purposes, when you're first starting off, think about it in terms of the ratio of sine and cosine. So in graphing this one, first hash mark over, or actually count 2 hash marks over. So 1, 2 to the right, and then 2 to the left. Negative hash mark there, and then hash mark there. This first hash mark for the parental function is just pi over 2. Why is that? Because that's going to be the first vertical asymptote, which causes the bottom of the fraction, because tangent is just sine over cosine. Cosine of pi over 2 is 0. And you can't divide by 0. So hence vertical asymptote. And of course, to the other side, to negative pi over 2, that's also a vertical asymptote. Because if you input this into cosine, which again, you could rewrite this as sine of x over cosine of x. If you put negative pi over 2 into the function, we're going to get 0 on the bottom. So we can't divide by 0. Hence, vertical asymptote. Right there. So we're primarily concerned what's happening in between. Why is this hash mark so nice? Halfway's between pi over 2. That's pi over 4. Because tangent of pi over 4 is positive 1. Arbitrary, put the hash mark right there. Positive 1. You know what? Let me put the hash mark. This is positive 1. This is negative 1. So for our tangent function, now let's consider 5 points. If you plug in 0 into our function, that's going to be 0 over 0, which is 0 over 1, which is 0. So that's point number 1, 0, 0. If you plug in pi over 4 into our tangent function, it takes us to positive 1, as mentioned before. And then if you do limit analysis, or you plug in values that are closer and closer to pi over 2, you explode upwards, like so. So connect 1 to 2 to end behavior of this motif. So something like this. Concave up. Now if we consider the other direction, if you plug in negative pi over 4, it gets us to negative 1. If you can do the limit end behavior analysis, it's going to point downwards forever. So something like this. That's not a very good graph. Something like this. Well, it's kind of frustrating. Something like this, yes. Alright. I try to make this a little more smooth, a little smoother. I made it look too much like a cubic function. It's not a cubic function. It does have origin symmetry though, so this is an odd function, which we're not going to cover really. At least not for now. So here's what's going to happen. We're going to take this motif and we're going to copy it across. So we'll take this motif, copy paste, and that's what's going to happen. So how do we know where to copy paste this one? Well, because the vertical asymptotes will be evenly spaced apart. So from the center of this graph, of this particular motif, how do we reach the vertical asymptote? It's 2 hash marks over. So count 1, 2, this will be the next one. I'm sorry. Let me say that again. From one vertical asymptote to the next vertical asymptote, it's how many spaces? 1, 2, 3, 4 hash marks, because of the way the hash marks have been laid out. That's why I like the motif of 4. So 1, 2, 3, 4. And because of the periodicity of trig functions, we're going to copy paste this motif right here, and we're going to plant it right between the vertical asymptotes, like so. And you could also copy paste the hash marks. So if you call this in the center hash mark, this is center, half of half, and this is half of half. So from this center, it's a 1 to 1 movement, 1 to -1 movement. And I hope that's clear. So central ideas, this one can be transformed into this ratio. You can think about the vertical asymptotes, and then you can think about plugging in optimal points like 0, 0 and pi over 4. This is all prior to shifts, of course. So let's practice graphing some tangent functions. Let me get the color. I lost the color. Alright, so suppose we're just graphing some basic functions. Y is equal to tangent of. Let's start with the basic shifts first, as usual. So we have x minus. It has to be in nice radians, so something like pi over 2 or pi over 4. And then on the outside, you could be plus any integer. It's typically the situation. So let's put plus 1. So something very easy. Just a horizontal shift and just a vertical shift, based on the tangent function right here. So x-axis first, the y-axis in the middle. That's why I like to focus my graph. 1 hash mark over, halfway's right there. We're going to copy paste this one real quick. Just for a nice scaling. Okay, and because this is a tangent function, this is an unmodified period change. So how do we reach the first vertical asymptote? It's if we input pi over 2. Not counting the shift just yet. So this is a consideration of the base tangent of x function only. This is where the vertical asymptote will be located. Let me put that on a different layer real quick, because we're going to have to shift everything over. So again, pi over 2 is the first vertical asymptote to the right. And then 2 hash marks over, this is going to be negative pi over 2. Will take us to the other vertical asymptote wall. And just considering the tangent of x function, 0, 0, pi over 4 leads us to 1. So let me put the hash marks first. This is going to be 1, not to scale. This is going to be negative 1, not to scale. So pi over 4 leads us to a ratio of 1 to 1 for a standard parental tangent function. And then end behavior explodes upwards. Connect them as smoothly as possible. Like so. So we're done with the right hand side. What about the left hand side? It's just going to be 1 hash mark to -1 hash mark. Explodes downwards forever. Something like that. Okay. And that should be good enough for the unshifted parental function. So what's happening to our situation? Two things are happening to our situation. We have a shift of pi over 4. It's going to be opposite land, so it's to the right, and then we have a shift upwards by 1 space. So let's keep track of the anchor points. So I'm going to put this as an anchor point, and this one, and so 3 points as anchor points, just to pay attention to this one and to that one. So when we do a shift, everything shifts, including the vertical asymptotes. So unlike the sine and cosine one, where we didn't have any vertical asymptote considerations, now that we do, any horizontal shifts also affect the vertical asymptotes. So everything gets moved over pi over 4, which is just 1 hash mark space. So let me label the hash marks before we do the shifts. Let me label them. So this is, again, this is pi over 4. This is pi over 2. Negative pi over 4. And then negative pi over 2. Because we're going to do a shift, let me put more hash marks. Copy that, paste that, just for even spacing. We don't really need it on this side, but let me just do it anyway. Okay. So now let us address the shift of pi over 4 spaces to the right first. So drag everything, including the vertical asymptotes, 1 space, 1 hash mark, because each hash mark is only pi over 4. And there it is. And then we're going to shift everything upwards by 1 space. So those 3 anchor points, keep track of them. They each move up 1 space. So the -1 gets moved up to the 0. The 0 ends up being at +1, and then the 1 ends up being at +2. So let me put 1 more hash mark for this one. And there we have it. Whoops, I cut it off. And then there we have it. We have the shifted graph. We are pretty much finished with this particular problem. But let's keep track of this. Let's test our hypothesis real quick. So this one right here is pi over 2, +2. So our graphical prediction, according to our hypothesis, if we input pi over 2, we should get an output of 2. So let's check it. So pi over 2 minus pi over 4, that's just going to give us positive pi over 4. Tangent of pi over 4 is 1, and then 1 plus 1 is going to give us 2, which is what we predicted. So now that we know that this graph is good, let us just copy paste this motif and repeat it over and over. Okay, this kind of bugged out a little bit. Let's delete that. So this whole thing will be repeated ad nauseum. So take this thing, copy it, paste it, try to make everything overlap perfectly. So this is where it is, with the third magenta point. The lowest magenta point to the left should be at 0, right? So put it on the x-axis. So something like this. It looks kind of a mess though, because again, this is hand-drawn. And since I copied the hand-drawn list, it just looks kind of funny. So if you paste it one more time, just overlap the vertical asymptotes. Try to do it perfectly as possible. I can't really do it though, so something like this. We're going to get the same repeating motif across between every single vertical asymptote pair. And that's how we graph the tangent function. So all the same rules apply. So if you have negatives, then that's just reflecting either across the vertical or across the horizontal. So let's look at that real quick. So y is equal to, let's just do one reflection. So 1 minus tangent of, let's do x minus, let's do plus pi over 2. So this is for our consideration. Let's do the x-axis first. There it is. I'm going to put 4 hash marks. This is already 1 hash mark. So 1 and 2. Let's copy paste this for consistency's sake. Alright. So we have 1 hash mark, 2, 3, and then we have 4. I have a feeling this is not halfways. That's fine. Do we have any modifiers on the x? No, we don't. So this is standard 0 for the standard position is going to be pi over 2 for the vertical asymptote. So vertical asymptote number 1 is at the default pi over 2 position. And just for consistency's sake, for future copy pasting, I'm just going to copy paste this one directly right here. You know what? I could actually correct this, right? If we compress, no, that's too skinny. I can't see it. That's fine. We'll leave it like that. So, standard positions of the vertical asymptotes. So this one's at pi over 2. And then this is at negative pi over 2. Again, understand why we have vertical asymptotes right here. Because this makes the cosine of the fraction into 0. That makes the cosine in the bottom of the fraction into 0. Which results in vertical asymptotes. Alright, that takes care of this portion right there. Let's consider the optimal points. 0, 0 for the standard tangent of x function, and then pi over 4 gives us to positive 1. I'm missing hash marks. Let me put hash marks. So that's going to be positive 1. Let me copy paste that one. So positive 1 and then negative 1. Just in case we need more points. Alright, good enough. So default movements, 0, 0 first, and then 1 to 1 movement. This is going to be pi over 4. And then close to the pi over 2, that's a vertical asymptote. As we approach vertical asymptotes, you always hug the wall. How do we hug the wall? By going upwards against the wall, like so. Just follow the trajectory of these ones. So from these trajectory, we want to get close to the wall, never crossing it, never touching it. So like that. And then we're good to go for that one. And then if we plug in negative pi over 4, that's the first hash mark, and then we move 1 hash mark down. So 1 to 1 movement. I'm sorry, 1, negative 1 to negative 1 movement. So end up down there and follow the trajectory, approach the vertical asymptote, but explodes downwards. Like so. And we're done with the parental function. This is just tangent of x. But now we need to consider the fact that we have a negative, and we have a shift number 1 and shift number 2. So in consideration of the fact that we do have a negative in front of the tangent, all it does is it reflects all the y values. So across the horizontal reflection, across the horizontal. So with this negative here, 0 is still going to be 0, because 0, if you reflect it across the axis, The default axis is still 0. But instead of being positive 1 hash mark to 1 hash mark up, it's now 1 hash mark to 1 hash mark down, because the y's are flipped. So down here. So follow this trajectory and get close to the wall. Again, you can just do crude limit analysis for this one. Something like that. And again, because it's this negative modifier, instead of being -1 to -1 hash mark movements, it's going to be 1 hash mark movement, and then 1 hash mark, I can't speak. -1, 1 hash mark movement to the left, and then 1 hash mark movement upwards. So it's +1 instead of -1. Follow the trajectory. Try to make this as smooth as possible. I can't do it. And get close to the wall, but never touching it, go upwards. So we are done with the reflection. Now we're tasked with 2 more things. Just have to do horizontal shift, pi over 2 spaces to the left, and then 1 space upwards. But how many hash marks is pi over 2? It's 2 hash marks over. All right. So everything's going to move 2 spaces, but I need more hash marks. So let us copy paste just a little more. So here we go. We're going to take the entirety, vertical asymptotes and all. Whoops. So take this entire graph, and we're going to move everything to 2 spaces, which is going to be 2 hash marks, which is equivalent to pi over 2 to the left. So my anchoring point for the shift right now is the one at the origin, 0, 0. So move it 2 spaces to the left. So 1, and then 2. Alright, so we've accounted for the horizontal shift, and now we need 1 more shift. That's going to be 1 shift upwards. So take the entire graph. The anchor point at this point is going to be the negative pi over 2, 0, the center one. Take that and drag it up 1 space upwards. So only 1 hash mark. So there it is. So that means that we've finished accounting for the shifts. Let me just extend this a little bit. And that is pretty much it for the motif. Let's copy this motif and then we'll paste it over. Kind of cheating. Not really cheating, I guess, just being quote-unquote efficient. So there it is, and then we can copy paste the motif and put it to the left. This is why spacing is very important for the visual. Alright. So that should be the graph for our tangent function. So if we're feeling particularly paranoid, we could always test it. Don't test the nodes, because reflections don't... The node tests don't discriminate between reflections. So let's test this point right here. That should be located at pi over 4, comma, 2. So that's the predicted point from our graphical hypothesis. So let us test that out. So if tangent of pi over 2 plus pi over 2, that's basically pi over 4. Tangent of that one we know is positive 1. 1 minus 1 is going to give us 0. Whoa. That means that's the prediction was wrong. Wait a minute, something's weird. Well, let me think about this for a moment. Yeah, something is not right. So that's why it's always nice to do these tests on occasions, just to make sure that the graphing is correct. Oh, that's right, I plugged in the wrong number. I'm sorry, I don't know why I plugged in pi over 2. We're plugging in pi over 4. Yeah, I goofed up. That's my mistake. So I even wrote pi over 4, but I plugged in pi over 2 for some reason. Okay, so this is our actual point. Pi over 4, we're expecting a value of 2. So adding those two up, right? So this one, unfortunately, doesn't match the denominator. So top and bottom times 2. So times 2 times 2. So that gives us 3 pi over 4. Okay, now that's better. Tangent of 3 pi over 4. That's in quadrant 2. So that's positive 1 to negative 1. So that is going to be negative 1. 1 minus the negative 1 that we just got does indeed give us positive 2. So this point is correctly predicted by our graphical hypothesis. So should be good. So now let's get to the period changes, of course. So suppose we're doing something like y is equal to 2. And let's also do an amplitude change. So let's do 3 times tangent of 2x minus pi. No vertical shifts because they're not that important, honestly. So let's just stick with this one first. So xy axis has been planted. Let us do the hash marks. So now that we have 2 hash marks, I'm going to copy paste these two. And they are perfectly spaced. Alright. You know what, let's copy it just a little bit more. That's how extra we want to be, right? Alright, there we go. Let me put the... How many do we need? We need up to 3. So let me put this as arbitrarily 1. It's not to scale. But it's not that important. Alright. Well, that's a fake hash mark. Hold on, let me delete this real quick. Alright, there we go. Alright, hash marks are in place. And now let's consider a few things, of course. So, this is now tangent of 2x. Bear in mind that the vertical asymptotes have been changed in 2 ways. Number 1, the x inputs have been modified by 2, so now we should be twice as fast to reach our vertical asymptotes. We also have a fake shift of minus pi, so let us first factor out the 2 from these 2 terms. So factor out the 2, we get x minus pi over 2. Close the parentheticals inside tangent. 3 amplitude. Okay. So what are we considering for the vertical asymptotes yet again? Well, there's 2 ways to do this. You could just modify the standard period change. The standard period for the pi is, the standard period for the tangent function, if you memorize it, is going to be pi. So you can just manually set 2x is equal to pi. And solving for x is equal to pi over 2. So this one is going to be the length of the period, right? But if you hate memorizing stuff, at least in the beginning, you can start off by just thinking about tangent as a function as a ratio between sine of x, but it's now going to be 2x, ignoring the shift for a moment, relative to cosine of 2x. So what are we thinking about? We're considering how do we make the bottom into 0. So what causes cosine of 2x to become 0? That's ultimately the consideration for the VAs. So what does that mean for us? Well, if we have interquadrant angle there and interquadrant angle there, so that's going to be pi over 2 plus every single iteration of pi. And k is going to be some sort of integer. So that's the default. This one leads to the default vertical asymptotes. But it's modified by 2x, so we force 2x to be equal to this nonsense. It should feel like a familiar strategy, because we've done this when we're solving for angles inside cosine functions. Okay, so plus pi k. So divide everything by 2, thus we get x is equal to pi over 4 plus pi over 2k. So this tells us that our default vertical asymptotes is going to be if k is equal to 0. That takes us to the first positive vertical asymptote, which is pi over 4. And then if k is negative 1, that takes us to our second vertical asymptote, which is negative pi over 4. Prior to any shifts, of course. So, default vertical asymptotes. Again, prior to any shifts, so this is only considering the fact that we have a 2 out in front. So if we go to here, first hash mark, second hash mark, that takes us to the first default vertical asymptote, and then 2 hash marks over takes us to the default other one. So this is going to be pi over 8, negative pi over 8. So that after considering the vertical asymptotes, we can now consider just planting the default parental function, which is going to be 3 tangent of 2x. So just considering this, ignoring the shift for a moment, let's just plant this one. We've already considered the 2 modification inside, so that's done. So let us take into consideration the graph of the tangent, which is going to be standard default 0, 0, so that's not too exciting. Well, let's put the vertical asymptotes, I'm sorry. So we have vertical asymptotes at the pi over 4 and negative pi over 4. Now we're going to do this as straight as possible. I'm just doing standard copy paste cheese strats. And hopefully that's going to be straight enough. We're going to take this right here, copy that, put that one over, whoops, right over there. Should be good. And then let's plant the anchoring points. So again, ignoring any shifts, just a standard 3 points. So we have the point at 0, 0. This one should be default 1. But don't forget, we now have an amplitude change of 3. So what would have been 1 to 1 hash mark if this is defined as 1 is now going to be 1 hash mark space to 3. And then following this particular trajectory, you just try to make it creep up along the horizontal asymptote, vertical asymptote. So it's going to get a little artsy right here. Oh, that's kind of bad, but that's okay. So something like that. So instead of being a negative 1 to negative 1, we have negative 1 to negative 3 hash marks, which is down there. Connect those ones as smoothly as possible. So something like that should be good enough. So it looks kind of funky So we'll probably have to truncate that if necessary. That's okay. So we've taken into account the amplitude. We've taken into account the fact that it's a tangent function. We only have one thing left to do. It's the horizontal shift of pi over 2 spaces to the right. Remember, this is not the true shift. You always must factor this coefficient from the both of those terms. So true shift is pi over 2 spaces to the right. How many hash marks? It's not 2 hash marks, because that's pi over 4. So this is why keeping track of the hash marks is very important. So not 2 hash marks, but 4 hash marks. That's pi over 2. So what we're going to do is we're going to take the entirety of this graph. Whoops. And then we're going to move it 4 spaces. So the anchoring point will be at 0, 0 for now. So take it 1, 2, 3, and then 4. So that's going to be true shift. So in other words, nothing has happened, right? It's ultimately the same period. Same motifs. So if we copy paste overlapping the vertical asymptotes, we can get the exact graph for the other, between the other vertical asymptotes. So that's nice. So something like this. And that's basically it for the graph of this particular function. Let's test a point. Don't test the nodes. Always try to test something other than the node. This is probably the easiest one to test out. This is positive pi over 8. This is positive 3. So that's predicted by our graphical hypothesis. Let's just test this out. So if we plug in pi over 8 into here, then we expect to get an output of 3. So this one, if you multiply those two together, we get pi over 4, and then pi over 4 minus pi. That gives us negative 3 pi over 4. Tangent of that one, that's unfortunate. That's in quadrant 3, like this. So that gives us a tangent of positive 1. Positive 1 times 3 is indeed 3. So the graphical hypothesis is consistent with the data, which means that this graph is probably good. If we wish to beautify this one, we could always truncate it. So I'm going to cut it off arbitrarily there. And there. And then now it's going to look gorgeous. There it is. So that's it for the graph of this one. I think I'm going to call it for now because my voice is giving out for some reason. So the next time, for the next stream, probably just going to be doing a bunch of graphing problems to review what we just went over right now. And then, unfortunately, there's not enough time to go over the reciprocal functions like secant, cosecant, and cotangent. They're mostly the same thing. You're going to see when we get there. And definitely we're not going to cover the inverse function until after all this nonsense is done. So I think that's it. You have yourself a good one, and I'll see you next time.